Give me a second. Let me set this thing up. Okay, we are live. We're recording. Everything is fine. So now it's ready. Okay. Good morning, everyone. I hope you had a good night and good morning breakfast, Pavel. Thank you very much. So we begin again. Just a couple of announcements. We're going to change the links, the shortcuts, dot space ones, so that then bhtom.space will direct you to bhtom2, right? Because that was on a popular demand request. We'll change that. There will be also another link, bhtom1.space. You want bhtom1, bhtom2.space giving bhtom2, but the bhtom without any numbers, it will make you, it will link you to the bhtom2. Okay? And please do use it, crash test it, especially this week, okay? So that we can fix it while you are here and you can give us feedback. That's the whole purpose of us being here. Apart from that, we're also here to listen to interesting talks, right? Yaro.
Thank you very much. Good morning. My pleasure actually to start this day, this morning session, and I will speak about symbiotic stars. My name is Jaroslav Merc, and I actually now work at the Astronomical Institute of Charles University in Prague on research of symbiotic stars. When I planned this talk, actually I wanted to speak about different things about symbiotics in outbursts, but then Gaia Science Alerts were very productive, so I will cover basically new stuff with symbiotic stars from Gaia Science Alerts in the last year. So just a yearly reminder what symbiotic stars are, because a lot of you actually listened to my talk previously, so just to remind that these are interacting binaries. Where one component is a cool giant which is losing mass either via stellar wind or Rozhen Observatory flow, and the second component is usually a white dwarf, but we have some symbiotic stars with neutron stars as well. These are very wide binaries in comparison with cataclysmic variables, for example, because the orbital periods are typically of hundreds of days to tens of years. So we are not speaking about hours, but more about years. And they are very interesting because there is plenty of things going on, and one of the things which are going on in connection with symbiotic stars are outbursts. So changes in brightness, and you can see that even very well with Gaia. I will talk about that. It's not only outbursts, which you will see in the photometry. Here, long-term light versus selected symbiotic stars, and you see that they are very complex. So in addition to outbursts, you can see some of them here, some active stages and outbursts. You see some variability which is connected with orbital motion, and you see the variability which is connected with pulsation of the cool component, and with hot component, and so on. In some cases, you see eclipses, for example, in this one. I borrowed this figure from my talk I gave in Krakow this year, because I tried to illustrate that the time scales of the variability we have in symbiotic stars is very wide, starting from minutes, somewhere, for example, for the hot component rotation and flickering, going up to decades in case of some outbursts, active stages, and orbitally related effects. So if you are interested in the short time scales, that not very much, Gaia is not very much useful for that. But for example, tests can do that, and actually I submitted a paper on test observations of symbiotic stars, so you can read, I hope soon, more about that. About orbitally related stuff I taught at EAS, so if someone of you was not there and is interested, I can provide my slides. And I will focus more on the outbursts this time. So basically, more or less, there are three main types of outbursts. Two of them, slow symbiotic novae and symbiotic recurrent novae, are that we somehow understand the physics of that. It's a thermonuclear runaway on the surface of a white dwarf. With set Andromeda type, which is the most prevalent type of outburst, so-called classical outburst. Then the models of these outbursts are still behind what we see in observations. But as I said, in a new online database of symbiotic variables, I'm maintaining the catalog of symbiotic stars. This is a prevalent type of symbiotic outbursts. And actually, from the number of about 300 symbiotic stars we know in our galaxy, about 1/4 of them were detected in some kind of outburst in the past. But still, with the outbursts of symbiotic stars, there are many questions connected, and I just selected some. With Zeta Andromeda type, these classical ones, we still need to understand the outburst mechanisms. With slow symbiotic novae, for example, there is a question if that kind of outburst is a transition from so-called accreting on the symbiotic star to shell burning symbiotic star, because we saw that in some cases this outburst actually started the classical symbiotic activity. And for example, with symbiotic recurrent novae, which is a very small group of symbiotic stars, but all of them are hosting quite massive white dwarfs. There is a question if symbiotic stars are and how good they are as progenitors of supernova 1A. So basically, then at the end, you want to see more outbursts of symbiotic stars and to see more outbursts to understand how symbiotic stars evolve and how they can contribute, for example, to supernova 1A. You can do that with Gaia. And this is actually some kind of summary of my last 3 talks at this conference in the last 3 years. Because with Gaia Science Alerts, we were able to discover symbiotic star in outbursts, this Gaia 18ADN. But we also discovered extragalactic symbiotic star in outbursts in M31. And last year I spoke about symbiotic nova discovered by Gaia, which is the paper is still in preparation, and that's the object file I need BH data to reprocess for. But also Gaia detected some known symbiotic stars in outbursts. So this is just a list that, for example, in 2019, that was a Gaia detection of symbiotic recurrent nova in outbursts, and that's actually very hard to detect because the symbiotic recurrent nova outbursts are very short in duration. So, for example, for this one, you basically have 1 epoch when Gaia observed that in brightness. But also then in 2020, there is a detection of a known symbiotic star in outbursts, another one in a small Magellanic Cloud, and 2021, it's again the detection of known symbiotic star, that's a 73 141 in outbursts. So Gaia can do that. Gaia did that several times more, and I selected some of the objects which were detected last year and this year to speak more about. So one of them is this one. Actually, that's a known symbiotic star. So it's also written in the comments that it's threatening a symbiotic star. You see the Gaia light curve from the Gaia Science Alerts webpage. So we did a follow-up. This was detected in April 2022. So actually before the last conference, but I have I spoke about something different last year, so I included this one here. So as I said, it's a known symbiotic star, but thanks to Gaia, we now know that this symbiotic star is showing outbursts, because this was the first recorded outburst of this symbiotic star. We did the spectroscopic follow-up to confirm that it's a Zeta type outburst, and the active stage of this object is actually still ongoing. So we obtained some more data, even with solved tools for this one. Then I had the idea that maybe if that was basically Gaia detection of symbiotic star in outburst, the first one recorded for this object, maybe in the Gaia Science Alerts archive there are some other known symbiotic stars which were detected in outbursts and were unnoticed basically. And yes, actually there are. So for example, this one, Gaia 18 CFA, is an outburst of a symbiotic star BL36, which was detected by Gaia, unnoticed by anyone. It was before I started to work with Gaia Science Alerts, therefore it's unnoticed. And we now know that this is another addition to the list of symbiotic stars showing outbursts. With this one, actually, the Qui Serpentis, it's a whole active stage, which is still ongoing until now for 6 years, which was not like noticed by the community and was not studied. And the final one is again an unnoticed outburst of this known symbiotic stars in 2020. So now we have at least like 3 more which are in the archive and were not studied because they were not noticed by the community. This one was after the conference, so this is addition since last year. This one was not detected actually in brightening, but in fading. But again, it's a known symbiotic stars, as also remarked in the comments. And what we did was again to do some analysis. In this case, we didn't do spectroscopic observations. We analyzed photometric data, and what we found actually that this is a known symbiotic stars for a lot of years. But this is the first detection of eclipses in that system. Before, there were some of the data analyzed, but unfortunately, all the time the eclipses were falling into seasonal gap. So basically, this is the only part of the eclipse which was visible in the data, and then basically nothing was visible. So now, thanks to detection by Gaia of the fading, we know that the system is eclipsing and it's showing the eclipses with the period we calculated. And for the analysis in this case, Gaia VPR detectors were very useful because, as you see, outside the eclipse and during the eclipse, there is a change in the continuum. So we know what is going on thanks to this very low resolution data. So this is the first detection of eclipses in this system. When I started to prepare the talk, these slides were not included because actually these are detections, two last detections from September. So this one is from September 21, very recent, when this object was reported to be an outburst. It's a known symbiotic star. The outburst actually was ongoing since April, but first of all, it was not reported in Gaia Science Alerts because you need 2 epochs for the report. And what is very important to remind everyone and our community as well is that this one was not reported by any other survey because it's a known symbiotic star, known variable stars. And if you have something which is known to be variable, surveys are usually not reporting that as a new transient. So we then can lose a lot of symbiotic stars in outbursts, and we are not observing them because we don't know they are in outbursts because they are not reported. And I just mentioned here another case which was not detected by Gaia. Actually, it was not reported by anyone to be in outbursts. It was just a coincidence that I was doing classification of symbiotic candidates, and I found out that this object is in brightening, and it's a symbiotic nova which is in brightening, and it was not reported by any survey which is doing the follow-up. So one need to keep in mind that if we have a variable source, it might not be reported to be a new transient. This one is actually quite interesting object because already Mariusz in 2013, when they were doing the analysis of ASA's data, they found out that it's showing periodic outbursts, probably which are linked with the Berry-Essner passage. So when the hot component and cool component are close to each other, we have an outburst. The behavior changed a bit. We detected 2 outbursts of this one, which are separated by 5 times the orbital period. And in between there is nothing, so it's very interesting to follow up this one. And the last object is also from September. It was reported to be a Myra in brightening. It's actually classified as Myra based on the study from 1940. It's still might be a Myra, we don't know, because you cannot see any pulsations in the light curve because it's a crowded field, so you just don't see what the cool component is doing. But actually, you see that there are something which is not Myra behavior, it's an outburst. And we did a spectroscopic follow-up, and we found out that it's a symbiotic star in outburst. So it might be the first symbiotic star discovered by Gaia with Myra donor, if the Myra pulsations will be confirmed. There is something present with Atlas data, so it might be there. It's definitely not a typical D-type symbiotic star. We don't see the very strong infrared access, so is that over question? There might be D-type symbiotic star detected by Gaia, so this is the very last object I have. It was detected in May. It's super faint, even in the brightening. It shows pulsations in the light curve. It's a very red source. There is an infrared access, so it's a very good candidate for D-type symbiotic stars. You see the position in the infrared color diagram, and actually those orange ones are other D-type symbiotic stars. So this one might be a first D-type symbiotic star discovered by Gaia. But we need a spectrum to confirm, and the star is actually in the most of the optical, it will be maybe 22 or 23 meters. Maybe the detection in infrared will be. It will be possible spectroscopically, but I'm not sure if there's an option to obtain a spectrum. So with this, I will conclude. So now there is a list of eight interesting Gaia Science Alerts we analyzed, and most of them are clearly symbiotic stars. That last one might be also a symbiotic star. So that's what I wanted to present, and as a last slide, I will thank you for your attention and show an advertisement. So if you're interested in symbiotic stars, we actually are organizing a conference next year in Prague on symbiotic stars, so you're all welcome to come. This is, I think that's the very first advertisement on this conference. We are working on the website, so stay tuned.
Okay. Thank you. Time for one quick question, and actually, see, Josh was first.
Hi, this is Josh. I'm an amateur astronomer, and I observed symbiotic stars for Ulisse Munari. They have been sent to the BH-TOM, and I can also provide my observatory, which I will present later today for follow-up observations if you are interested. Just drop me an email.
Yes, definitely. For example, that object which might have Myra or might not have Myra would be interesting to as an object for a follow-up, because surveys just don't have the good resolution for analyzing that particular star.
Okay, this is so loud. Sorry, we have to move on. I can't use it. Sorry. I'll switch on the next talk, which is going to be, where is it? It's just too loud. The mic input is too loud. Okay, Dawid Moździerski, Jaroslav.
Yes.
Floor is yours.
Good morning. So my name is Dawid Moździerski.
One more thing. Can I ask the speakers to speak from the other side of the screen, so that then there is camera there, so people watch your face instead of that.
Okay. So I work in Wrocław University, and I'm happy to be here, and grateful to the organizers for this opportunity. And with my talk, I would like to convince you that it is worth to observe targets in open clusters. Why open clusters? So I think anybody who is interested in how stars work should be interested in open clusters, because we can make, for example, we can make some very useful assumptions for open clusters. Like we can assume that members of open clusters are at the same distance to the observer. They share the same composition, chemical composition, and the same age. And we have opportunity to study stars in wide range of masses. And massive stars are frequent members of these objects. And I'm one of astronomers who is interested in massive stars. Why? There is many good reasons for that. One of them they have significant impact on the chemical evolution of the universe as a progenitors of supernovas, and in their interiors are extremely high temperatures and pressures. So we have opportunity to study matter in the conditions unreachable in Earth laboratories. It's very hard to look inside the stars. There is not a lot of methods to do it, but one of the most promising is astroseismology. And if you want to do astroseismology of massive stars, we need pulsating massive stars. Fortunately, there are pulsating stars like Beta Cephei type and SPB, but the crucial problem is correct identification of modes, because we cannot see the surfaces of the stars. So we have used some clever methods to identify modes. And if you want to do this, we need a lot of photometry and as continuous as it is possible. So campaigns are very useful for this. Also, spectroscopy is is needed for this. And if we find many pulsators in one cluster, there is a possibility for so-called ensemble astroseismology. So we defined it as simultaneous seismic modeling of more than one star, which uses constraints on parameters resulting from the membership of these stars to a distinct stellar system, like open cluster. And there was some approaches of ensemble astroseismology. This is not a new thing, but I think we use as much information as it is possible from our observations to do it with our own way. So our approach is constraining a cluster age and mode identifications at the same time, iteratively. And the mode identification is in such method, we called it ensemble identification. We made it for one cluster, NGC 6910, with success. This is a very young cluster. From the photometry, it was estimated that its age is about 6 million years. And there was 9 Beta Cephei candidates. Of course, we need a lot of photometry. So we conducted a campaign, observational campaign, and we were able to get about 20,000 CCD frames in B filter and a couple of thousands of CCD frames in B and I filters. We need at least 3 filters for the good photometric identification of modes. And also we got some spectroscopy, about 150 spectra for a few stars for this cluster. And as a result, we detected 37 intrinsic frequencies for these stars. They are visible on this panel here. And what is nice for us, what was nice is the frequency spectra arranged according to the decreasing brightness. So the mass of stars, because they are in the same open cluster. So we have the brightest star here, and going down we have fainter stars, so with lower mass. And this is exactly what we could expect for P modes. So we guess that it is good target for astroseismology. So how does it work? With our approach, we at the start with estimated parameters of the stars from spectroscopy and photometry. And these are error boxes of these stars on the plane of log G and log effective temperature. And then we used seismic models. We started from the star number 18 because it showed radial mode, and radial mode is much easier to model theoretically, and we used just the range of temperatures for this star, for star number 18, and we got a constraint on age of these seismic models marked here. And this range of age we use for constraint of seismic models for the rest of the stars. This is just these are the models for star number 16. For star number 14, we could only use evolutionary models. So here are in gray color, and we made it for the rest of the stars for 27, 25, 41, 34. As you can see, for 41 and 34, there is very narrow range of models, which is good for estimation of parameters, and for 38 and for 36. So we got narrow ranges for log G of the stars from such modeling. And as you can see, as you can notice, there are some overestimation of log G for less massive stars and underestimation of log G for more massive stars. As a result, we, after 2 iterations, we got this age here, and with pretty good error, because from conventional isochron fitting, we are usually getting error like 30–50%. So it's good for the future. And also, of course, apart from the parameters of log G and log temperature, we got more parameters from seismic models, and we are able to revision of instability strips. These are the state-of-the-art instability strips for beta Cephei and SPB stars, marked with red dashed line and green dashed line. And it turns out that one of our beta Cephei stars is outside of the instability strip of beta Cephei stars. So this is kind of theoretically and observational hybrid conclusion that we have a star outside of instability strip. So the theory has to be correct. And in fact, this is the least massive star of beta Cephei star known. Unfortunately, we didn't know yet. The seismic picture isn't the same always. For NGC 884, you can see the schematic frequency spectra on the right side. There is no visible, not visible such progression of modes. So we don't know yet what is going on there. We have to do ensemble star seismology for this cluster to figure it out. And we have some more targets now. We are finishing analysis of NGC 637 cluster. These are preliminary results from a campaign in Yanko Observatory. Here is a picture from our observatory. On the right side, there is the color magnet diagram for this open cluster, and as you can see, we found there some couple of beta Cephei stars on the top of CMD, and they should be useful for ensemble star seismology. There is also interesting group of frequencies here, which might be rotationally splitted frequencies. And the next targets on our list is NGC 63293 from the southern hemisphere, Western 1, and double clusters. But these stars shows a very low range of variability. So it's not triggered Gaia alerts, but as a byproduct of our search for massive pulsators, we found also very interesting stars in young clusters, which shows monoperiodic variability. And these stars are probably primary sequence stars. There are also stars with irregular variability on the right side of this color magnetic diagrams. And so we are interested in these stars also. We are interested in connecting parameters from ensemble asteroseismology of beta Cephei stars, which are also in these clusters, with these primary sequence stars. So this is the point where we would need Gaia alerts, because Gaia can sometimes can detect variability from such stars. So I don't have too much time to go into details, but I hope that we will be able to use the network of BHNO for some to get some observations of even massive stars.
Okay. Thank you, Dawid. I will make a comment here because, well, Gaia Alerts is one of the sources of targets of interest, while your targets are your targets of interest. So just feel free to add them to BHNO and we will observe them whenever we can. However, I just noticed one challenge. Our system is not tuned for clusters. Because I guess you're interested in multiple stars, so you would add, say, 10 targets to the system, which are just next to each other, right?
Yes, yes, it's something that should be solved. I hope, because it is advantage for observers, because when they observe just small region of sky, like open cluster, they can make science for 10, 12 targets.
And we're actually working on the system so that we process not only one target of interest, but we also process all the stars in the fields. So, well, having your particular science case in mind, we will tune our system so that you can just you can add one target to our system, and then we'll observe the whole field.
It would be,
and then you don't need Gaia alerts for that. If there happen to be one of them alerting, we will find it and we will let you know. Yeah. So it works this way. Right?
This will be excellent, I think, for other systems.
But I think you already, while waiting for our system to be updated, you should add one of your stars of favor to the system, and we can already start observing it, right?
Right. Okay. Thanks.
Any other questions, comments?
A question about rotation and metallicity. How do you deal with that when, well, we model the things, right? But then this massive star rotation is pretty big. And I guess you include it somehow, but in which step do you?
Yes, so the rotation makes big problems with non-radial modes. But for radial modes, it's not that that big problem. So this is why we started from radial modes, and some assumptions for rotational we can get from spectra. So we need spectra for some members.
Okay, thank you, Dawid. Let's move on. The next speaker is already there. Zsofia, the screen is yours.
Okay, can you hear me?
Yes, we hear you. We see you almost there.
And my screen is visible, or yeah?
Yes.
Okay.
Yes.
Great. Okay, so I can start. Good morning, everyone. I'm Zsofia Nagy from Konkoly Observatory, Hungary, and I will tell you about Gaia alerted eruptive young stars. And so basically, this talk is going to be about what happened since last year's Gaia Alerts workshop. I'm going to focus on low mass pre-main sequence stars, and these sources are already visible in the optical, but they are still accumulating mass from their environment, from the envelope onto the disk, and from the disk onto the stellar surface. And part of this accreted material is removed by outflows. So in these systems, the most important process is accretion, as it heats the disk and increases the luminosity of the star. And you can see here also an artistic sketch of this scenario with the disk and the accretion streams and the central star. Accretion is important, however, it's not so easy to understand, as it's not a smooth process. It's inhomogeneous in space and time, and from time to time during the evolution of the source, it can vary by orders of magnitude, as you can see here, due to instabilities, thermal or gravitational instabilities. And of course, accretion is not the only process that we need to take into account here. There are many other processes which affect the variability of these pre-main sequence stars. And there are many different timescales, as you can see here, from hours up to a century. And the typical variability amplitude is lower than 1 magnitude. However, in cases, the amplitude can be as large as like 6 magnitudes. So I'm actually going to be focusing in this talk on these sources with larger variability amplitudes. And just to point out, the two main processes are accretion, which are shown in blue color, and circumstellar extinction, which are shown in red color. And sometimes it's not so easy at first to distinguish between these two processes. So eruptive young stars, which are cases of episodic accretion, are important to understand because we think that most young stars, or actually all young stars, go through this kind of process during their formation. So if we want to understand star formation, we need to understand episodic accretion. We can do that by studying these eruptive young stars, which were historically defined into two classes. One of them are the long-term outbursts, FU Orionis type objects, or FUORs, which show outbursts on a time scale of decades up to a century. All these sources are still experiencing their outbursts, so we don't actually know the time scale. We are still waiting for one of these examples to start fading. And the other type is EX loopy type objects, or XORs, which show outbursts on a time scale of few months up to a year. And these outbursts are repeated once every few years. But of course, it's not just their light curve, which can help us distinguish between these two main classes. There are also very different spectral features. Typically, XORs are seen in the spectra of XORs are seen in emission, and in the spectra of FUORs, we typically see absorption lines. And also there are other types, intermediate classes between FUORs and XORs. This is something that we are currently trying to understand and explore all the different types. As I mentioned, this is an important scenario, these eruptive young stars and episodic accretion. However, we only have about 50 examples of such stars, so it's really important to identify new sources, which is where the Gaia Alert system comes in. We are looking for typically two kinds of events. One, where the VSOs are brightening, so the brightening of candidates or already known VSOs, in order to discover new eruptive VSOs, but also we are looking for VSOs which have shown a long-term bright state. If they are alerted because of a fading, it's because of, as I mentioned, all the FUORs that are known are in their bright state, so we are looking forward to seeing an example which is about to end its outburst. When we see an interesting Gaia alert, we check for it in catalogs, in VSO catalogs, like those by Gábor Marton. If it's not in these catalogs, we collect all the available information. We check for SCDs, for infrared access. We look at color diagrams, collect all the archival data, infrared and optical. In some cases, it's not easy because the distance is uncertain. In that case, we try to investigate whether it can be related to any star-forming region. But of course, the main confirmation where we can really classify these targets is the spectroscopy optical and near-infrared spectroscopy. So we use a lot of different telescopes for these follow-up observations. They are listed here. And I need to mention that what happened since last year's Gaia Alerts workshop is that we started also using BH-TOM for our work. So just to give you a very brief summary of what we have done in the past few years, we have found more than 100 eruptive ISO candidates and measured spectra for more than 30 of them, and photometry for even more than 30, I would have to count. We found 2 XORs and 2 FUORs so far, and 2 other eruptive ISOs, which cannot be classified as either FUORs or XORs. And we investigated some other ISOs which turned out to be not eruptive. So I will show you some examples in the next few slides on what happened in the past 1 year since last year's meeting. So this is Gaia 21 ELV, one of the targets that we worked on. This is a known young star, which has observations already from the 70s, and sometime in the 90s, it had an outburst, and it was still close to the outburst state until, say, around 2020, and after that, it started fading, quite quick fading, about 1.2 magnitude over 18 months. So this was in the Gaia Alert system. And first of all, what we needed to figure out whether it's a FUOR, because there was no confirmation of that. There was no spectroscopy for this target, and also what caused this quick fading. So we measured spectra, optical and near infrared as well, with VLT X-Shooter and Gemini, and we compared it to the spectrum of FU Orionis and found that it is indeed a FUOR. It shows all the features which helped us classify, for instance, P Cygni profiles, triangular shaped H-band continuum, and so forth. But what caused the fading? To investigate the fading, we looked into SCD models at different epochs. We used the typical approach, a steady optically thick accretion disk with a constant accretion rate in the radial direction. And we found out that even if the accretion rate decreased since the brightest state, the rapid fading, which caused the Gaia alert, was most likely due to increasing extinction. So we are still looking for a FUOR, which is about to end its outburst. The other target which we looked at is a work by my colleague Michal Shivak. It's Gaia 21 BTY. It's a really interesting target. Over a few months, it brightened by almost 3 magnitudes when we took its spectra. However, later it turned out that in the optical, after about half a year, it faded almost back into quiescent, not quite, but almost. However, the spectra are really typical FUOR spectra. So what's happening here? Since then, we know that the source is still bright in device data. So what we are thinking is that there might have been some large-scale inhomogeneous dust condensations in the line of sight, and that's what caused the fading in the optical. But maybe it is a FUOR and the outburst is still ongoing and it might brighten again in the optical. We will have the answers in time. We need to investigate this further, but it seems like a really interesting target for now. Another source, which a paper on this was just submitted by my colleague Eleonora Fiorellino, is Gaia 18 CJB. It shows a long-term brightening event. It brightened by 5 magnitudes over about 8 years. It's still in the bright state and it's still slowly brightening. So it's a light curve which is similar to FUOR light curves. However, when we measured its spectra, we found out that the spectra are really similar to XORs. We measured the accretion rate, and the accretion rate is also in the range of XORs. So at the moment, we think that this is an example of eruptive ISOs which are which represents an intermediate case, so somewhere between XORs and FUORs. And this is something really, really new, very, very much work in progress, Gaia 23 BAB. So this target alerted the Gaia alert system early this year or sometime in March. It brightened by 2 magnitudes. And we can see in the light curve that there was another event earlier in 2017. So this light curve resembles that of XORs, which was the conclusion by Michael Kuhn in the research note. They collected all the available photometry and other information. However, they did not have spectra to confirm this. So that's what we did. We measured spectra with the NOT. This is the comparison between the spectra of EX Lupi and Gaia 23 BAB with the NOT. Since then, we observed another spectrum with the IRTF. And based on our preliminary results, this indeed is an XOR, also confirmed spectroscopically, but this is still a work in progress. I'm gonna have to figure out the accretion rates and other parameters, so this is ongoing. And another kind of work that we started doing in the past 1 year, this is still quite new. We collected all the YSO Gaia alerts, and we did some selection of the events which are probably accretion related. And so these events are about 400. These are shown in this plot. We want to see how the timescales and the amplitudes are distributed. And at the moment, it looks like that there is the distribution is closer to uniform than in these distinct groups, which is in the literature. So we are still investigating this. Of course, there is a limitation on the lower end because of the 30-day cadence of the Gaia light curves. Anyway, so this is work in progress and will probably result in interesting conclusions on YSO timescales and amplitudes. Just to summarize this, so we are studying Gaia alerts in order to investigate eruptive young stars, and we are doing this with spectroscopic follow-up observations. In the past 1 year, we found at least 4 interesting targets. We found a new viewer, Gaia 21 ELV, which was fading, but still not at the end of its outburst. Then there is Gaia 21 PTY, which shows an XOR light curve in the optical, but a fewer spectrum. So this is another interesting target. And the other situation is 18CJB, which shows a fewer kind of light curve. However, its spectra, it's similar to XORs and its accretion rate as well. And there is Gaia 23 BAB, which is an XOR candidate, and I'm currently investigating this. And we are also working on a larger sample to identify some trends in the timescales and the amplitudes of these accretion events. So this is what I wanted to share with you today. Thank you.
Thank you. Thank you, Zsofia. Your science case is really perfect, I think, for our telescope network, since your targets are, first of all, they're being found by Gaia, which we like, and then they're bright and they're very long term. So if there is a network of telescopes ready to observe, at different timescales, I think this is most suitable. So I hope you're most encouraged to add your targets, which you are currently studying, which are currently ongoing, to the new VH top system, and I'm sure people here will be very interested in observing them in their free time. Okay, questions to Zsofia?
I have a question to you.
A question to me.
Have you fixed the issue with BAB?
I will look into that at the coffee break. BAB is the one I'm going to look at. Thanks. Okay?
There's a hand up.
There is a hand up. And it's Josh.
It's me again, yeah. I would like to tell to the speaker that actually, you should also look at the AVSO database for targets of your concern. For instance, I'm observing Gaia 19 FCT since years, and also YSOs in the Orion nebula area. So like V555, Ori, and others. I mean, most of them are in the AVSO database. And again, I offer my observatory for follow-up observations. I have a presentation after coffee break, and then you can see my email address. Thank you.
Okay, thank you. This is a great suggestion. I'm going to look into that database as well and will contact you.
Okay, any more questions, comments? No, I don't see any. Okay, thank you, Zsofia, very much. And let's move on. I need to take over the screen. Just a moment. The next speaker is Yanko Nikolov, and the slides are coming. Here. Here. And there you go, this is the control. Okay, just press forward.
Thank you very much. My name is Yanko Nikolov. I'm working in the Institute of Astronomy and National Astronomical Observatory for Gaia Photometric Science. I will talk about spectropolarimetric observations with one of our instruments, and presentation was the research about recurrent RS Oph.
I'm sorry. Now?
Okay, thank you. This is the two-channel focal reducer Rozhen with a wide variety of observing capabilities like one-band and normal filter imaging, sleek gold dispersion spectroscopy, for recurrent interferometry, imaging polarimetry, and wall dispersion spectropolarimetry. Here the instrument attached at the 2-meter telescope at Rozhen Observatory. Okay. I would like to present our sample of observing hypopolarized standard stars. With blue, you can see the degree of polarization. Red curve represents the Sierkowski wall, and these dots are cutoff value of the standards. But most important, be careful with the standards, because in our sample of 10 observing standards, 2 of them show the degree of polarization. So this is our last research. Recurrent nova RS Oph here is similar to the recurrent nova that hosts red giant and massive carbon oxygen white dwarf. In this picture, you can see the degree of polarization in blue. This is the interstic polarization of RS Oph after correction of the interstellar polarization. The observed polarization is dominant. The interstellar polarization is dominant component of the observed polarizations, and here you can see strong depolarization effect across the emission lines. With red is the normalized Stokes E parameter or intensity, and in the left, Western observation students after the last outburst. On the left, you can see first 3 observations taken on day 2, 6, and 7 after the outburst. And you can see that the degree of polarization increased over the shortest wavelength. We have 2 scattering processes, scattering by electrons, wavelength independent, and scattering by dust, wavelength dependent, when the degree of polarization increased over the shorter wavelength. And we interpreted this as dust within the first night day after the outburst. And depolarization effect means that the scattering region is inside the emission line region. It's easy to interpret the results when we think not in the degree polarization but in polarized flux. And here you can see in the middle row the polarized flux in blue on day 2 to day 7 after the outburst. On the left, you can see in day 2 with different velocities, but most interesting is a different position angle. The position angle is determined by the orientation of the scattering type. So this is the one more complete collaborators in 2017. And when the ejector of the white with the pre-existing material, here is the region where the this formation and where the gamma and rays come. RS Oph may be one of the most studied records now, and here you can see the asymmetry after the 2000 hours in radio, in X-ray, and this is bipolar eject infrared after the outbursts in 22. This is our schematic view of our spectropolarimetric observations. We also call bipolar flow with slowly expanding equatorial torus, where the position angle is 90 degrees, and fast bipolar outflow. And this is the most interesting part of this research. Was suggests that similar geometry, those and polar scattered region, presented in agents in RS Oph, can produce similar spectropolarimetric signatures. On left, you can see the infield model of agents, and spectropolarimetric signature of RS Oph is similar to type 1 agents, where the position angle is aligned with the radio axis. So a conclusion, I would say that future spectropolarimetric observations of other novae will be essential not only to for illustrating this formation, as well as the early evolution of the asymmetry of the material. So, if you are interested in this work, you can download from here. And if you have questions,
Okay. Thank you very much, Mateusz. Thank you. Any quick comments and questions we have?
What is the limiting magnitude for this?
Depends on the target. If you have a vision line, the limited magnitude may be 30 magnitude for our spectrum. We many photons for spectropolarimetric. How big is that? And I also observed two Gaia alerts in this telescope, spectrum, and limited magnitude was 15, 16. One of them was Gaia 19 BPG.
Okay, thank you very much. I hope we can see more data from this telescope in BHTOM as well.
Yeah, Stefan will talk about this telescope.
Yeah, good. Very good. Okay, thank you. Let's move on to a presentation from Zoom this time. Andrii, you're with us?
Hello to everybody.
The screen is yours. Just
Okay. Is it okay now?
yeah, we do see everything. So yes, you can start.
Okay. Hello to everybody again. It's my pleasure to be again a part of Gaia community now, and I would like to tell you or share with you some information about our investigations. Mainly, it's cataclysmical variable, and most of them SU UMA type stars. We are trying to combine observation facilities that have Gaia and other like Assassin and Assassin, Atlas, Lacer, combined also with AFSO data, and get as more as possible data about the objects to make our observational plan more or less suitable for observations in order to get as more data as we need. Also, while using black hole TOM, sometimes we get some problems. Here you can see in red that for unknown reason, data from ZTF are not depicted or are not visible on the image. Probably someone can explain, but as for me, it will be good if everything data will be collected in the same plot. About structure of our investigations, will talk my student a bit later, and I just put you attention on services we used for determining main parameters of cataclysmical variables, and would like to share with you our new investigations of new Gaia alert. It's Gaia 23 CER. It was supposed to like a cataclysmical variable. We were thinking about its observation for a long time because the object is not very good, for example, for our observations in Zlesniki, because we have no possibility to resolve these two objects. It was a very big doubt for me to observe it or not, but finally we obtained a light curve during 2 hours, 2 or a little bit more hours, and received such a result. Here we can see clearly see a wave curve with eclipse. The remarkable thing is that on the images the star was disappeared at all. It became invisible, fully invisible. But on this light curve, due to this situation, because of two stars are very close, we have a magnitudes. It's like a sum. Magnitudes of two stars. So here you can find a magnitude of the second component, second star, which near on the sky, near to this star. Also, we continue to monitor this star and obtained another light curves in other days, and found that the shape of main light curve with days changed. But the main discovery was after observation of this star using 2 and 6 meter telescope in Crimea in filters, and we discovered that this star have an eclipse with 5 magnitude deep in BVR and only 3.5 magnitude in I. So taking into account all data we gathered together, we can assume that we discover a new polar star. And for now, we are looking for possibility to obtain spectroscopy and polarimetry for this object, just to get more information about its physical parameters, as well as we need a good time resolved photometry for the eclipse to find its shape. Because with our facilities, we have no possibility during eclipse duration 7 or 8 minutes approximately for the star of 22 magnitude, or for the object with 22 magnitude in V, obtain more than 2 or 3 points. But to provide a good shape, we need some more data. So if anybody interested in polars and can help with observations, it will be very good cooperation, and we are open for your suggestions. And as a small conclusions, I would like to thank the whole Gaia team for such objects, and my colleague told that Gaia 23 CER is an amazing gift from whole Gaia team for CV people, for people who study cataclysmic variables. Thank you for your attention. Sorry for so short talk.
Thank you, Andrii, very much. Questions, comments? Well, we thank you for picking the targets and to prove Gaia is useful. We thank you for that as well. I don't see any questions, comments, but I will definitely I'll look here. I'll definitely look up into this target you mentioned where the ZTF data is missing. You should actually check now BHTOM2. That might work better, and the ZTF data could be for the target. Try it there. Try adding this target to BHTOM2.
Okay, thank you.
Okay. Thank you, and I think we should should break here and move to the coffee break. Thank you, and let's meet 11:15.
The name of based on the
Hi Josh, we are there with a little delay. I'm moving you to the main screen now. And you can start sharing. Okay, hello everyone. Again after the break, and we begin with this session with Josch Hambsch. Yeah, we see your screen very nicely. Can you say something?
Yes, hello.
Yeah, we do hear you.
Can you
Okay,
hear me?
the floor is yours.
Okay. Okay, thank you, Łukasz, and giving me the opportunity to present the follow-up of Gaia Alerts from my private observatory ROAD, which is called Remote Observatory Atacama Desert, which also says that it is in Chile. And as we speak, it is still running. I'm a retired nuclear physicist, and I'm a member of several amateur astronomer organizations like AVSO, BEV, and GEOS, and the Flemish variable star section I'm the leader of. I cannot move forward. Okay. So ROAD is at San Pedro de Atacama at Space Ops. The landlord is Alain Mauri. Before the pandemic, it was very touristic with restaurants, hotels, internet, power, and water. Especially internet is very powerful and even faster than sometimes from European destinations. It's at 2,500 meter elevation, and as you know, Chile has exceptional number of clear nights. I'm there since 12 years, and every year I average between 312 and 345 nights. So the ROAD is off-the-shelf equipment. It's on a 40 centimeter f6.8 optimized Alkirkham from Orion Optics from the UK. So it sits on an ASA DDM85 direct drive mount, so a very fast mount. The biggest change I made in May 2023 when I changed my FLI 16803 CCD camera to a CMOS camera from QHY. It has 16-bit and it is much more efficient than the CCD. I run it and at 4x4 binning to reduce the file size, and I could reduce my exposure times most of the time by a factor of 2. So I recommend for those who are thinking about putting a camera on their telescope, look at the CMOS cameras available nowadays, the 16-bit ones. I use standard software, MaxMDL, CCD Commander, Lesser Photometry for photometry calculations, and VNC or AnyDesk for remote access of the local PC. So nightly observations are in the order of 30 to 50 targets. And normally, the most of them are in snapshot mode for normally 2 images per filter, not all the time BVRI, sometimes only BI or BV or whatever combination. And most of the images are taken in time series. And there, due to the fast mount, I switch between targets. So I normally observe 3 to 5 stars simultaneously, so every few minutes cadence. But of course, if there is a request from you guys on special target, I can also observe them solely during several hours, like I presently observe in clear filter the Swift J1727.8 minus 1613, the possible black hole candidate. And the data I normally send to the AVSO database. So I recommend you also to check the AVSO database. And I recommend Łukasz to make it available via the BHTOM2. So this is an aerial view of the site. The landlord is actually showing the tourists which come to San Pedro, the night sky during night, most of the time. And this is his main income. But you see also that there are, I don't know if you can see the cursor, that there are several observatories, and this is an image a few years old. I'm not alone there, and other people are also putting the observatory at this site. So this is the view of the clamshell observatory. So if I would have a dome, I would have weared out all the motors and gears, because I move around very fast on the sky. As I said, 3 to 5 targets simultaneously, sometimes only a few seconds of exposure time due to the efficiency of the camera. And of course, the nice background of the Milky Way, because the Milky Way is up above you on the zenith in summertime, when it's winter in the southern hemisphere. So now follow-up observations, for instance, Gaia 20 FNR, which was already mentioned during previous presentations. So I've followed it for more than 500 nights. The gap here was due to the seasonal gap when the star was behind the sun, and I have restarted it, but probably I will stop after the present observation season, because it has more or less leveled out, and it's no longer of interest. Then Gaia 21 CCU was also very interesting and very fast. Micro lens. Here this is a close up of the very few, few 50 or so nights where it really went up, and within 2 nights it went down, and the micro lens was over. Gaia 22 BPL was also mentioned. I have followed it over 200 nights. Nicely, in 22, I covered the peak of the event, and now it is more or less again towards the end of the season, end of the season as well, and also end of the observing period. Gaia 22 DKV was also mentioned. I observed it for more than 320 nights. Again, you see a nice coverage in 3 filters, and the peak was nicely observed. Gaia 23 BAY observed over 170 nights. It's a new microlensing event from this year. And you see even in the different colors, you see even structure after the event has stopped. So there might be a pulsating star in this system, which shows it in the light curve. Gaia 23 ATS was also followed, again, a very fast event, only in the order of 10 nights was the maximum, and then it dropped again towards the quiescence, more or less approaching quiescence level in the recent night, in the recent time. Then by Prismec, I have been recommended to observe HD 133729. I observed it in BVR eye filters. These are the previous more or less 12 nights. There is some fluctuation, and I wait for Prismec to give me guidance for changing the exposure time or changing something in the observations. And of course, not only Gaia alerts are taken at ROAD, but also like the recent black hole candidate Swift with this house number. I observed in 4 colors, BVR and clear, and you see in the insert that there is some fluctuation over one night in the light curve, which is nicely seen. The exposure time is 15 seconds in clear, and the magnitude is in the order of 13. So that shows you the possibility of the QHY or CMOS cameras. And also young stellar objects were mentioned just before the coffee break. I observed them for the HOIS project, hunting outbursting young stars. This is a project run by Dirk Fröblich from University of Kent in the UK. I observed Gaia 19 FCT, which was mentioned for now the fourth year. Also Gaia 19 EYY for the fourth year. With each time there is an outburst. And EUY 21, Gaia 21 EUY. So yeah, so far has not much of fluctuations. And yeah, the road highlights. So as I said, I'm an amateur astronomer and a retired nuclear physicist. My first Nature paper was in 2016 on the first white dwarf pulsator RS core. And I can announce that the second Nature paper will come out on October 12th, so next week, on this star Assassin 21 QJ. And of course, I have lots of further collaboration, intensive nova observations, intensive cataclysmic variable observations, symbiotic stars were mentioned. And I think, first of all, as a nuclear physicist, I never had a Nature paper because it's very difficult to get one in nuclear physics. Now I have two as an amateur astronomer, and I have more than 125 papers with co-authorship, which you can find in archive searching for my name, which I think are more than I ever had in my professional career as a nuclear physicist. And for those of you, so as an amateur, it's possible to do science with variable stars, and participation in alerts and requests for observations are the key to the success. And as mentioned, I have many collaborations and more than 125 read papers in archive. And if you are interested to reach me, this is my email address, very simple, M31, that's the Andromeda Galaxy @telenet.be, because I live in Belgium and I'm German, but I have my telescope in Chile. So, and like last year, I would like to plea to Łukasz to give via email priority targets, because not all the time I can I look at the BH-TOM and or BH-TOM 2, because I don't have really the time to do so. Thank you.
Okay. Thank you. Thank you. We've been collaborating with Josh for quite a number of years, and he's been one of our most active observers. So thank you, Josh, for that. Questions, comments to Josh? I was pleased to see that you changed your camera from CCD to CMOS, and actually we checked with Shank, and the data quality has improved, which is a really good thing to see, because we might encourage other observers to do the same. So can you comment on this? How are you happy with your new camera?
Yes, I'm very happy. As I said, first of all, it's 16-bit. The pixel size is very small, 3.7 something micrometers. So 4 × 4 binning gives you 15 to 16 micrometer pixel size. Before the CCD, I binned 3 × 3, which had a 9 micrometer pixel. So it was 27 micrometer pixel size, just to be able to reduce the amount of data to be stored and transferred to my private computer here in Belgium. Yeah, the efficiency is in the order of 90+% QE. So yeah, it's really the future of yeah, CMOS has the future taken over of CCD. I can only recommend to go this way.
Okay.
And it's much cheaper.
Exactly, right? That's a good point about it as well. Okay, thank you, Josh, very much. If you could stop sharing the screen so we can move on.
Yes.
Okay, I see Kristina is already there. Kristina,
Hello.
hello, if you can start sharing your screen, because you're visible on the big one here. Okay, the screen is yours. Kristina, please.
Hello, my name is Kaziemova Kristina, and I'm student of Taras Shevchenko National University of Kiev. We present the results of the optical monitoring of the selected objects from Gaia Alerts, which were observed at the observational station. All the data were obtained during our observation were uploaded to BH-Tom. Also, a detailed review of historical data when was done for some object using other observational facilities. We used AZT-8 telescope for observations. Please find detailed information about this on the slide. Here we can see the general light curve of the cataclysmic variables to demonstrate the values that we can find using Assassin, DTF, Atlas, etc. data using internet, and which we can find only due to observations, our own or partners. For example, we can determine the period of super humps. For example, our recent observations of Gaia 90 CUU during super outbursts. Duration of normal or super outburst, mainly from our own observations. Here the graph shows the light curve of the object Gaia 19 CU, which is in a super outburst on which the super humps are clearly visible. The approximate amplitude of the super humps is 0.2, 0.3 magnitudes, what is typical for stars of the SU Samars type. From internet, we were trying to find super cycle time between two super outbursts. Sometimes estimate the duration of a normal and super outburst. For the objects from this table, we were able to determine the amplitude during outburst and super outburst duration. More data were collected for the next objects. Here we obtained also periods and periods of super humps. And conclusions. So in the course of the work, a certain list of Gaia objects was studied to determine various parameters and classify objects. Also, by analyzing the dates of the object outbursts, it was possible to predict that the next outburst of the Gaia 19 CU object can be expected in the following date range. So we are ready for catching next super outburst for this object. Thank you for your attention.
Thank you very much, Kristina. Time for quick comments, questions. Anyone? Zoom? Beautiful light curves, a lot of data, and I assume the long-term observations, do you also do the very detailed light curves? Do you also submit them to BH-Tom or not? We lost it.
Yeah, lost connection.
Okay, we can continue discussion on Slack. Right, so let's move on to the next speaker for a short poster presentation. Mateusz, are you there? Okay.
Yes, I am. Hello, can you hear me?
Yeah, we see you, we hear you, but we don't see your screen yet.
Ah, yeah. But that might become important. Now you should, I suppose.
We do, okay. The screen is yours.
Perfect. Hello, everyone. My name is Mateusz Bronikowski. I am a graduate student at the University of Nova Gorica in Slovenia, and I would like to briefly introduce you the GoChile telescope. So first, what is GoChile? It's a joint project of SPICA, which is a local Slovenian astronomical journal, and University of Nova Gorica, which is the university I work at, located near the Italian border. It's the main telescope is a 40-centimeter telescope, and it is located in the RS Observatory in Chile. Now, the telescope, technically there are two telescopes. The first one is a 40-centimeter RCT telescope with RG and B filters. There's also H-alpha and O3 if it becomes necessary. And there's a second telescope mounted on the same mount along with it, with a larger field of view, mostly used for astrophotography. The telescope is remotely controlled. It's not fully robotic, at least yet, although we are currently looking into whether we should integrate the telescope into the LCOGT network. And the time on the telescope is shared between observers from SPICA and from University of Nova Gorica. Now, the use cases of the telescope are bright targets with a limiting magnitude of around 17th magnitude. We can observe targets with high cadence because time on the telescope is available very often. This week, for example, we had time on the telescope to observe targets for for Black Hole Tom every single day, every single night, except for 2 days on which we only had half of the night. It's great for observing southern targets. So northern targets, there are more telescopes currently following up from Black Hole Tom, but we can supplement those observations with southern targets. Now, I would also like to point out that the telescope is also used for outreach, education, and astrophotography. Our university organizes summer schools for students. There are also scientific projects where students of our university do some scientific projects. Like we had one student, Martina Larma, who performed observations of a few microlensing events from Black Hole Tom and analyzed them. You can see also here pictures of that were created by people from the SPICA magazine. And yeah, we are currently starting to ramp up observations for Black Hole Tom. So in conclusion, the telescope is great for high cadence follow-up for bright southern targets. And if you want follow-up from our telescope, just reach out to us or put your targets on Black Hole Tom and we will observe them. We are currently automating the whole observation process as much as possible. So we will be observing Black Hole Tom targets a lot in the coming days, weeks, and hopefully years. Thank you.
Okay, thank you, Mateusz. Great. So you see, Josh has shown you what can you achieve in the southern telescope. So that's your goal, I hope. Przemek has a question.
Yes, it is. Thank you.
Hi, Mateusz, Przemek here. I have a question about automation. Will it be possible for us, for BHTOM, to directly call for observations from a telescope? So will there be any API for us to be able to connect to it?
So you mean for Black Hole Tom to directly tell the telescope what to observe?
Yes, just trigger the observations remote.
Well, with the current setup, it's not really possible. Of course, if we do decide to join LCOGT, then that would be handled automatically, I believe. But as it is now, it's not, at least with what we're currently using for automation, it's not really possible. It would require a lot more work than what we're currently doing. So, this is something we can look into in the coming months, but not something we can do right now or like in the next few days or weeks.
Okay, thank you.
So,
shoot me a message on Slack and we can talk about it a bit more.
okay. So the only way now is to send you an email, right?
An email, or you can reach out to me on Slack. I am on the Black Hole Tom Slack, so we can always reach out there.
Okay, very good. Thank you, Mateusz. Let's move on.
Thank you.
Give us the screen back. Thank you. And now we have a short presentation from Stefan. Just a sec. And
can you give me the click?
it's over there, and your slide is somewhere here. Okay, Stefan.
So, hi everyone, I am Stefan from Rozhen Observatory, and since I have 5 minutes to present my poster, I'm going to use them to promote my workplace, Rozhen Observatory Bulgaria. So, Rozhen is located in southern Bulgaria, very close to the border with Greece. The closest beach is about 50 kilometers from the observatory. It is located in a place with very low light pollution. You can easily see the Milky Way, you can see the Andromeda Galaxy with your naked eyes, and it's a very good place for observations. And the average seeing is between 1.5 and 2. So these statistics are from 2008 until today, and on average we have about 150 observational nights per year at Rozhen Observatory. And we have a 2-meter Ricci-Chrétien-Coudet telescope, which has 2 main instruments. One is Cholera 2, which I'm going to talk about later, and the other one is a Viper-fed shell spectrograph with a resolution of about 40,000. We also have a couple more instruments. We have that 60-centimeter telescope that every observatory in Central Europe has. We have a Schmidt telescope with a large field of view, and we also have a new 1.5-meter telescope from NASA, which had its first flight a few months ago, and it is still in test phase. So, I am an operator of the 2-meter telescope, and very often I work with the Fourier 2 instrument, and it can be used for all kinds of stuff. It can do imaging with 2 CCDs simultaneously in 2 bands. It can do narrowband imaging. We have a whole lot of boxes of filters. So it can do for peripheral imaging, it can do polarimetry, spectropolarimetry, and most importantly, it can do low resolution long plate spectroscopy. And sometimes it happens when I'm an operator to have a few hours of free time on the telescope, and while the way do I observe some transients from Gaia. So last year we had a couple of hours free on the telescope, and we decided to test the limits on that long slit spectroscopy modes of the instrument, and we decided to obtain a spectrum of this transient, which we measured to be 80 in magnitude. And as you can see, the spectrum is not very good looking, but we can see the H alpha there, and we measure it with an equivalent width of about 8 angstroms, plus or minus 2. And this instrument can be used for follow-up, spectroscopic follow-ups of transients. And for the next semester, I hope that we're going to have a TOO program, which would likely be allocated about 30 hours for the next half year. And our director is almost convinced that it is a good idea to buy a new spectrograph for the 1.5-meter telescope. So if you know somebody who makes low-resolution spectrographs, please talk to us. Thank you. That's it.
Okay. Thank you very much. We do know someone. We will put you in touch with that. So the Sprat instrument
on Liverpool, yeah.
Yes, so this has been spreading. Actually, Sprat was designed within Opticon not long ago, and now it's growing. The community of Sprat users is growing. Now it's in OHP, and also we've been contacting people from SOAR and other telescopes as well. So definitely this is a spectrograph to go. 1.5 meters is perfect. I wanted to ask you about this 1.5 meter telescope as well. How available it is? In terms of
you
time?
have to ask the director.
Okay.
I don't know yet.
Okay. We should come and visit you. And the beach nearby. Thank you very much. Okay, let's move on. Karolina Bonkowska is next. Let me find your slides first. Yeah, we can start talking. I lost my cursor. It's coming. There you go.
It's working, yes, it's working. Okay, good morning, everyone. I am Karolina Bonkowska. My talk is actually the talk of my student, Dawid Moździerski, but he was not able to come to Malta, unfortunately, due to some kind of sickness. So I will summarize his small project, which he done during his bachelor degree studies. The motivation for actually investigating very well active dwarf nova ER-UMA was the renovation we had in our institute in Pilwnice. Recently we recoated all mirrors in both our telescopes. These are the photographs from the 60 centimeters telescope on which the Bartek conducted observations. On some photographs you can even spot the Paweł Zieliński, who was involved in all the steps of the procedure, which ended successfully, because we managed to gather very good data. Just like a very short reminder about cataclysmic variables, closed binary systems containing white dwarf as a primary and usually main sequences are as a secondary. The source of many interesting increases in brightness is the accretion of mass creating the accretion disk in the systems with the smaller magnetic field, and the hotspot which is at the edge of the accretion disk. And as I mentioned, Ursa Majoris is very active system for which we conducted some observations in March 2022. 5 subsequent nights during the super outburst. I have to point it out. This is this part. And apart from some other nights when we tried to catch this super outburst, we weren't that fortunate as in March 2022. But these data allowed us to test the telescope and its possibilities after the renovation. So with this clear manifestations of these tooth-shaped oscillations known as super humps during the super outburst, we could conduct some further analysis, and also with the presence of the super outburst itself. What Bartek did was 2-part of analysis. On the left panel, you can see 2 best super outbursts selected from a VSO database. There is almost 30 years of observations of the stars. Some of the super outbursts were very poorly covered, but some of them were excellent. These green Bezier curves are fitted to the super outburst, which allowed us to precisely calculate the super cycle length, so the duration of the how many nights are between one and subsequent super outbursts. And the same we did on the plot on the right side. The purple color is the Pilwnice data from the smart super outburst I mentioned before. The orange data are the data provided by the satellite. This is what we obtained thanks to Przemek Mikołajczyk, who extracted from test database. So great thanks, Przemek. And we calculated again super outburst, super cycle length, and for many super cycles we could calculate is there any change in terms of 30 years of observations of Ursa Majoris. The first publications discussing this star, there was a clear voice about that super cycle length, that it is rising, so it means that the accretion rate between the components it decreases, because when the super outbursts happen rarer and rarer, the mass transfer have to decrease. But as you can see at the last 2000 or 2000 days, it is not that obvious anymore, so it is definitely worth to monitor the star longer. And what Bartek also did is he investigated this presence of super humps. He calculated the periodogram, found the frequency of the super humps, he checked the amplitude, the changes of amplitude of the super humps, and he calculated O-C diagram for the data from Piwnice. And also the same analysis from the test data. We were a little bit unfortunate with this data set because the most interesting part of the super humps is usually at the middle and late stage of the super outburst, and we have a gap in observations here, but still it was worth to conduct the analysis. For this, we also conducted period analysis day by day, even with this 5 nice gaps of the observations here. We able to track some changes in the periodicity of the super hump period. And this is what was done also not only to obtain these values, but to check the evolutionary state of cataclysmic variables. In this plot, on x-axis you have orbital period, and on the y-axis you have something what is known as a period axis. It's a dependence between orbital period and superhump period. And usually active stars like Ieruma are located on the left bottom corner. It is still true based on the old, almost 15 years old data, the red dot and the newest data from Piwnice in TeS. What we observed is that we don't see like big changes because data from Piwnice and TeS are on the top and bottom of the middle measurements from the 10 years ago or 15 years ago. So this cannot be interpreted as some kind of significant change in the period axis. So probably we need some more data for this star in the longer time of observations. And we investigated the star not only to test our telescope in Piwnice, but I would like to highlight you a little bit the next step of our project. What we would like to do is to finally fit in the program, so observational radionet program. So we would like to do this kind of analysis, which was published by Molly and all in 2017. It was simultaneous radio observation performed for another star, SO Ursa Majoris. And these black dots are the radio observations from ArcMinute multi-Kelvin imaginary two-dish instrument located near Cambridge. And the green dots are the AAVSO observations. And what was pointed out in this paper, that there were some kind of flaring activity. The most surprising one, this is this huge flare at the end of outburst. And the source and explanation for this is actually quite a puzzle. We know that there can be some kind of dependence between accretion and jet manifestation in this accreting system, but we still don't know what is the mechanism. So definitely this kind of observation we would like to perform. So please stay tuned, conduct for us some photometric observation, especially when we will be doing the radio observations. Thank you very much.
Any current questions? Yeah.
Thanks. I'm just curious what the brightness is in the radio component.
In the radio, they had this. You mean the brightness, the visible brightness? During the super outburst, it was like 12 magnitude.
The radio.
I don't know. I have to check.
You don't speak radio.
Yes, not yet, but I'm learning. So.
So I have a question about the plot with linear regression in the superhouse. I think I already asked you this one, but from what I understand, it should be the time should be rising, right, over time. So
yes,
that's what you show here. Couldn't you fit any other curve? Because it seems that there is some kind of projection here, but why linear?
we just make it linear because that was the prognosis which was assumed for this object, yes, that it should be increasing linearly, like quite rapidly.
They all should,
even
right?
faster, yes.
They all should, but you have a decrease at the end.
Yes.
So are you considering to discuss any scenarios that could give you an effect like this?
Yes.
So that would be a third body in the system, or?
No, the third body not, but we are trying to investigate more of the systems and check whether there is some kind of maybe more complicated sinusoidal change.
Thank you.
So why error are not sure? Why say that the error associated with the ESC
are so big? Because sometimes these dots are not for the single super outburst, but they are being, for example, like for 100 or 1000 days, just to show that, for example, activity for 3 years was that super outburst cycle was around 43 days. But for some super outbursts, you have a clear beginning and you can estimate very nicely when was the first night of super outburst, but for some other, you cannot. So that's why the error bars are rising.
Okay, thank you very much. And now let's move on to, let's now speak some radio, right?
Let's speak radio. So I use this for the...
Yes, please. So just press the right arrow, that should do. So Ilse is going to give an overview on what's going on in Hungary region.
I'll try. So, I'm not the only one that's entirely out of my comfort zone here, which is quite reassuring. So I will talk a bit about time domain science with EVN. My home base is Jive, and before I go and explain exactly what all these acronyms mean, this week has so far been a little blast from the past for myself, because I started my career in microlensing, actually observing in the late 1990s for the Planet collaboration, and this was in a time when it was not by default that you would actually appear on the papers, which is why my name is somewhat separate from the actual expert in the field. But it was good fun, and it was really nice to see that this has progressed, and I'm really impressed with the work that's been done in this field and the black hole system that exists for uniform processing of data. This is definitely something that we're still working on very hard in the radio domain. So let me take you on a little bit of a journey of acronyms. The first acronym is the EVN, the European VLBI Network, which has an acronym in it itself. So VLBI stands for the observing technique that we use, very long baseline interferometry. You can forget about that. Just remember that it basically means that we're tying up telescopes around the world to make one very big virtual telescope. And we do this because we want to beat the diffraction limit. You're on the radio, you're very long frequency, very long wavelengths, so you stop seeing a lot of things get logology in this way. But by increasing the distance between your telescopes and tying them up, you're no longer limited by the size of your single dish, but you're limited by the largest distance between your radio telescopes. That's your baseline. And this is what we do with a very loose definition of European nowadays. So the hub of the telescopes is in Europe. There is one in Toruń that you may be very familiar with. But we also work with telescopes in Asia and even in South Africa. And when we want to do global VLBI, we use even the VLBI network in North America. So we can track sources for 24 hours, a full day, as they move around the Earth. Now this is the instrument that we use. And the institute that I'm based at is JIVE, the Joint Institute for VLBI, ERIC. The JIVE Institute is basically there to promote the EVN, to support use of the EVN, and to promote VLBI science. That's our core business. We also do technological development. We're the central organization for the EVN, EVN, which means we make sure the data from all the telescopes comes to us, we correlate it, we add up the signals for all the telescopes, you can actually do science with it. And since April 2015, we are on ERC. Now, what is quite interesting that this is very recent, the whole technical field is still fairly young. I've seen telescopes pass by here which were 70 years old, 80 years old. Field BI as a technique exists for 55 years. So that's fairly recent. So below here you see the 6 flags of our member states. We've got 2 observers as well. The fact that we are in ERC has made things slightly easier for us, but still not perfect. We're still struggling for finances like everybody else. We are part of the ORP project to make acquaintance with the optical astronomies and also to start to learn how we can optimize the processing of radio data and maybe add it to facilities like the Black Hole TOM and how to automate observations with EVN, which is quite a challenge. So what do we actually do? If you would want to observe with EVN, basically what you can do, if you have a brilliant idea, you come to us and we help you with setting up the proposal, with the technical part specifically, which can be quite tricky. At the end, we also need you to do the data analysis. We help you with the data analysis, calibration, and then imaging. Field BI techniques are not a very straightforward thing. I wouldn't say they're rocket science, but they definitely require expertise. That is not a standard thing, so we help you with that as well. We will not write your papers, but all the steps in between, the scheduling, the correlation, the verification, that is all done as a service for you. So you don't need to be thinking about all these aspects. Basically, you do the science. That's what is the purpose. So I'll try and explain a little bit about the capabilities, and I know we're getting close to lunch, so I don't expect you to remember all this, but I'll list the website where you can find all the information afterwards. So these are 3 of the bigger antennas. Unfortunately, I should have included pictures. The sizes range from a few tens to 100 meters. The Ellsberg one on the left here is the biggest one, and therefore also the most sensitive antenna in the EVN. And the baselines, the distances between the antennas range from a few tens of kilometers to 10,000 kilometers, and we're working with Chinese and Asian stations. It's a heterogeneous array, so we do not own the telescopes, we do not have much control over what the telescope owners do with their systems. We depend on them to collaborate nicely with the EVN, but if they say no, that's up to them. It also means it's a bit slow, we cannot be on target within a few seconds. And the response time, as I said, is slow, but also the fact that we observe not continuously throughout the year, because these telescopes are from institutes that also want to use them as limitation. So the frequency coverage, this is the frequency from 1 to 22 gigahertz roughly. We can observe at higher frequencies, shorter wavelengths, but then you lose about half of the telescopes because they don't have the receiver at this frequency. And even within this frequency range, there are fairly distinct frequency bands that you use. Not all the telescopes cover the same number of bands, so in some cases you'll have a little bit more, some cases you have fewer. This also affects the baseline length that you can use. And we use different observing techniques. The 2 most important ones is that data is shipped by hard drive, the old-fashioned way. But we also use e-field BI, which means that data is sent to us by glass fiber links, and it is stored up to the point that we can have all the signals from all the telescopes in Jive, and it goes into the correlator in real time. So this observing technique also means that if you want to have your data really fast, e-field BI is what you'd like to have. So in regular mode, we observe 3 times per year in blocks of 3 weeks. And we have got 10 days where we do e-field BI, so roughly once a month. That means if you do time domain science, your cadence is at best once per month, if you're lucky. So all this information is on the EVN website, evnbi.org, if you want to know more about this. What kind of science do we typically do? Well, we look at compact objects, because we are having a very large baseline, we are sensitive to very small items on the sky. Also means, because we do not fill the complete virtual dish, we are also not sensitive to very big things in the sky. So everything that is extended towards larger scales than your shortest baseline can sample, you will not see. Things get invisible for you. By default, this also means they're sensitive to relatively high energy sources. So there is a very natural link between high energy physics, astrophysics, and the compact radio sources, because these physical processes produce the same types of emission. And it gets a bit trickier when you go to optical data. Not everything produces optical emission. To give you an idea, if you're an extragalactic astronomer, what type of skills we are sampling, we are resolving roughly a milliarc second, which at the redshift 12.1 means 2 parsecs in a galaxy. Redshift 1 it is 8 parsecs. Thus it is really the innermost parts of the galaxies that you're looking at. Now I really like time variable sources because they have so many 3-letter acronyms. So listed a few here, there's many, many more. And in the next part of the talk, what I'd like to do is to give you a bit of an idea what kind of science we think is interesting, but what I would really like to know after the talk is what kind of science you think is interesting. Carolina just mentioned already the cataclysmic variables, which is why I asked how bright is this source, because that is of importance if you would like to do EVN observations. But first, one more caveat. We do not provide instantaneous images. So it's not a point and shoot CCD camera. You have to do some work for this. And you may remember this image. I think it's about the most famous interferometry image that's around nowadays. I'm part of the Event Horizon Telescope collaboration, and this, of course, was a fantastic thing to show to the world. And everybody now believes that this is the image of a black hole. It's not. Actually, it's an average of hundreds of images. And each of these images was vetted extensively to make sure that it fits the observations. So mathematically, you could say all these images are unique images of a black hole. And we did a very smart imaging, averaging step, lots of scientific discussions on how well can we actually produce this and show the world this one image. And we needed to do that because you can only make the first image of a black hole once, so you want to make sure it's absolutely done right. So luckily for you, you don't have to go through this in general if you do your EVN type of observations. But what Event Horizon Telescope has done is really been a revolution in imaging for VLBI techniques. So with that caveat in mind, let me move into some of the science cases that I selected. This is a selection, so basically from my own point of view, and also this is not my field, so please bear with me. I hope this gives you some ideas. So the first one up is the colliding binary star system. And in optical, here on the left, you can see that because the stellar winds are being pulled away by the rotation of the stars, you get this fantastic spiral-like structure. But these winds also collide right between two stars. And that is what you see on the inside, the little blue blob is the collision area where these two winds clash into each other, and that emits radio frequencies. So the two stars are shown in yellow just for reference to know where they are. We do not actually see them in radio, we just know that they should be there. And right in between is this collision region. So this can teach you something about the physical conditions in that region and the impact even on the stellar evolution by this wind region. Another thing of interest is quasars and the microquasars, especially X-ray binaries. X-ray binaries are of interest because they accrete, and we think that the accretion process is very similar to what is happening in active galaxies, but because the masses are much smaller, they evolve much faster. And they are a lot closer, so we can actually see a lot more detail. So by studying the microquasars, we can learn something about the big quasars. For example, on the left you see 3C279, one of the first quasars where we determine superluminal motion. Material gets ejected, and you see that it takes a couple of years before you start to see the evolution of that jet. On the right is the microquasar. The same process there takes over a year or less. So much, much faster. And therefore also the scales are about a few hundred times larger, makes it a lot easier to study. An interesting thing that I've not heard here, I'm not sure if they do emit an optical, but I think they do, gamma ray bursts. They have now recently been associated with, in this particular case, neutron-neutron star merger. So first, the gravitational wave event was detected in 2017, and a few seconds later, Fermi detected the gamma ray burst, and has later been confirmed to be associated with this gravitational wave event. And there was follow-up done throughout the electromagnetic spectrum. But what was interesting is that the radio and the X-ray light curves on the left here did not peak exactly when they were expected to peak based on the physical model that people had at that time. Radio follow-up make sure that we now understand a little bit better what's happening. So what actually happens, you have the merger. First, a shell of material is ejected, and then a jet is formed. This jet bursts into the material that was ejected before, and it was not always clear whether the material would choke the jet and therefore it would disappear, or whether the jet was strong enough to drive itself out of that cocoon. And here you see on the right 4 squares. The top left square is the actual observation with the EVN, and in the insert there's a slight enlargement. The other 3 are models. The top right model is a successful jet, so the jet breaks out of its cocoon, and the bottom 2 are choked jets at different inclinations. And the similarity between the actual successful jet models and the observations is really striking. There is no way that a choked jet could make that kind of radio structure in this source. So they were very convinced. We see a jet breaking out of this cocoon, and that teaches you something in that the new physics and physical models for these gamma ray bursts. Something that is definitely not familiar, because they do not emit in optical, but they illustrate the power of an instrument like the EVN, are fast radio bursts. These are very short-lived, very bright flashes of radio emission, and most of them are a one-off, so we see them only once. But a few of them have been generous enough to repeat themselves, which makes it possible for us to actually point the telescope and just wait for a very long time and hopefully see something. And you only know that, of course, after you've received your data, gone through the correlation process and made images. We don't know what they are. That's still a fact. We have found by now, there's been a few hundreds, thousands of them by now. There's been dedicated instruments to detect them. Still, the physical origin is not clear. The EVN was essential to localize the very first repeating FRD. This is the actual data. So you see here 4 blue crosses, 1 or 3 blue crosses, 1 red one sort of in the middle. These are 4 distinct flares of order a microsecond, millisecond, that were detected with the EVN. So we can resolve that level of time with the EVN. You can see that it's slightly elongated because the way the telescopes are positioned, you cannot resolve as much detail in all directions. But we do detect the flares, and the red one is the average position from the 4 different flares. You also see the contours, which mean there is continuum radio emission. So the source is flaring, and there is a process producing constant radio flux. Now this source was also detected in optical. There's HST images here on the left. It's in the dwarf galaxy, and it's associated with the star-forming region in that dwarf galaxy. So that was already interesting. People started to make all sorts of models about this. Then another one was detected in a ground design spiral, also in the star-forming region, so it was still associated with young stars. But then one was detected in a globular cluster, so a region where you typically expect older stars. So no uniformity whatsoever, and the jury is still out on what's actually happening in these things. So, a step closer to home, this may be more familiar to you. This is studies of massive star formation. So regions where really massive stars, 10 to 100 solar masses, are formed. And in this region, molecular lines are pumped into laser emission. So it is typically SIO lines or water lines. And in this image, you can actually see that the blue dotted area is the observation. Everything else is an artist's impression to give you a bit of an idea of what's going on here. The first observations showed these maser lines in a sort of circular orientation around this massive star. A later observation shows that they have expanded into a more elliptical shape, and the idea is that this is the star that's excavating a region around itself because the emission pressure is just pushing material away from it. Now, these maser lines have been detected also in the fluors and exostars that we have heard about this morning, so that might be another very interesting project to explore further if they are of interest. So coming back to my own field, active galaxies, we've also heard about OJ287, and here I illustrate again the improvement of the Event Horizon Telescope imaging technique. So this is not an EVN, this is actually the high-frequency big sister, the global millimeter field, the IRA, observing at higher frequencies, so 3 millimeters. On the left is the classical way that we would do radio imaging, so you see blobs. The brightest one is the central area where we expect there's 2 black holes. The other 2 are the jet emission. And with the new EHT imaging tools, we can actually start to resolve these things into much more detail. And you can see in the core what looks like a disk structure, and the jet itself is clearly bent, which is what you would expect if there is a double black hole system. You get this helical jet spinning away like a corkscrew essentially. Another hot topic in active galaxies is the association of the jet emission, or the very close areas, very close to the central regions, with neutrinos. So statistically, this has been very strong evidence. So that's the paper by Levin et al. The Russian team is doing this. But associating individual sources with a particular neutrino detection is still extremely difficult because we do not have sufficient time baseline. And this source shows this very well. So the red dots are 3 frequencies observed in 2013, and the blue blackish dots are the same frequencies observed around 2020. And because these sources are also variable intrinsically, you can't really tell if the difference in flux is related to a neutrino event, or if there's simply an increase in the accretion rate in these things that we happen to pick up. So this is ongoing work, and this is also something where we hope that higher cadence of radio observations can help a lot. And if you wonder, why do we look at 3 different frequencies? Well, this is just to make sure that we're actually looking at the centralmost regions of these objects. They all look like little blobs. If you look at the higher frequencies, you start to see a little bit more detail. And you also see that there is a stronger component and a weaker component, but to know which one is actually the core, the centermost region of your active nucleus, you need to see the difference between these frequencies. If it's flat, that means you're looking at the core. If it's a jet, you would typically see a much steeper change in the flux between these frequencies. So that's why at least 2, probably 3 frequencies really help you there. Oh, yeah, that was about to happen. So what I'm here for is to collect and talk about new ideas, especially for the time domain science field with EVN. We can do very high time resolution. We're not as good in the cadence yet, but we are working on that. And one of the things that may be of interest for you is that next year, as part of the ORP project, we are dedicated to have a call for proposals open that includes multi-facility calls. So just one proposal will get you access to this whole list of telescopes. So the EVN is included, also eMerlin, which is an interferometer in the UK. LOFAR, this is the low frequency interferometer throughout Europe, so that gives you access to megahertz, a few tens to 100 megahertz roughly. And a whole bunch of optical telescopes that can also compute these. So one of the things that I'm personally interested in, and if you have ideas about this, is complementing black hole tone with radio data. I was already quickly looking into this after Łukasz's talk, and this is still quite tricky. And also the link with the high energy is a very natural thing for radio astronomers. So triggers of the colibri system and the target opportunity options that we have at EVN, but also other radio telescopes, might be potentially very interesting to get a faster, quicker response time for target transient events. So if you want more information, you can scan this QR code, and that will get you to the page where you can subscribe to the EVN Tech newsletter, so you make sure you get all for proposals in your mailbox. There's also a user-supported Jive email address, and there's a few, for all the other telescopes I just listed, you can contact them as well if you know people working there. And as long as I'm here for the rest of the week, you're welcome to come talk to me.
Okay.
So, thank you.
Thank you very much. Thank you. Question, Solomon. Nada first, and then
So maybe it's too specific question, but see the brightness that you showed, the AGNs that you observed, and since it's your topic, I was wondering, do you have any observations of the AGNs that don't have like normal variability but have really big increase? I don't, changing the phasers or anything else. Do you see the changes in radio as well?
You mean the very optical, and then you see
Yes.
a radio? Yeah. Well, that's interesting you asked this question. We actually tried to get a proposal in based on the Gaia Alerts. That was not successful, but it would be very interesting to start tying this up closer. So I did some literature search before writing that proposal. There's not a whole lot of information there. There's some individual sources like the famous BLAC that are monitored consistently, but for the AGN as a population, there's not tons of information on associated variability and colorimetric. So that would definitely be an interesting thing to do. Yes.
Thanks a lot. I have two questions trying to understand the turnaround time and the time scales involved for TO observations. So you mentioned that you have this 1 day of the online mode. So I'm trying to understand what's limiting this. Why can't we expand that to the full 3-week period, for example? And then the second question, if you want to trigger a TO-like observation that would then only be scheduled in the next 3-week block, okay, within this 3 week, if you by chance find an interesting source within that block, can you still change the schedule, or is it all fixed due to technical reasons?
Yeah, those are very good questions. I'm not the expert on this. I'll try to use my best answer. So the days are pretty much fixed because we need to agree with all the institutes that own the telescopes that these days they will be available for EVN observations. There is a mode that we're working on that's called EVN Light, which ties also into the ORP work, where we basically have the opportunity to have fewer telescopes, so less sensitive array, but with a quicker response time. And ideally, when we have something like Black Hole Top, we can basically say the telescope, a set of telescopes is available, let's trigger an observation and they get to do it instantly. But we're not close even to that. So for the moment, if you have a TO trigger, you notify the operations people in Jive, and they will schedule it for the next upcoming EVNBI day. And usually, we're lucky in that sense because radio emission is generally slow, so it takes some time for it to brighten, and it's of course days, weeks. So typically, we do capture the signal when it's there. If you think of something very, very new, I think it's possible up to a few days in advance to change the schedule, but it becomes harder and harder as it goes because we do need to make sure all the telescopes are looking in the same direction. So each telescope gets a list of targets and times that they're supposed to look at the target in advance. So that's your hard limit when that's sent out. Does that answer your questions?
Why only 1 day?
Why only 1 day? Because of the telescopes also require their own observations. So this is what was agreed with the EVN as a network that they would provide to Jive for operating the system.
So EVN separately gets the proposal call. So is it also possible to do this, to give some proposals through your institute, JNB, or the proposal should be through EVN also?
Yes. Yeah, Jive does the operational side, so we organize the reviews, but the proposals themselves go to the EVN. Sometimes it's not always clear what the boundaries are, but this is clear.
Yeah, I'm definitely going to encourage everyone to come up with science topics. So the AGNs Nala is doing, and then viewers, youngsters as well. If we could coordinate some kind of
TDs are already a part of
TDs,
the,
yes. There are people who are working on them already.
Yeah, there's Stefan Stefanov is one of the people doing this. I remember the viewers and experts, we had a talk by Agnes Ospa a couple of years ago about ALMA results from them. They were really interesting. The cataclysmic variables, when they have radio emission, would be very interesting. So definitely room for a lot of interesting projects there. Yes.
Yeah. Something what will interest me, and I mentioned it to you already, the archives, the time domain archives. If we could plug it in to be done, that, well, for now we already have the first catalog of radio built in, so if there is a radio source, we will know, right?
Yes.
But there is time domain data somewhere, and how can we access it?
Yeah, that's a good question also. So the radio community has very heavily invested in the virtual observatory access. So we have the data accessible, at least the basic information is accessible through the virtual observatories. The actual data, the visibility data that we get out of the correlators, you still need to get that from the archive. But if you want to know if a source has been observed with the EVN, or even LOFAR is also in there, you just can go through these VO services. I was just checking that earlier this week to see very quickly if I could find time information in the VO services. That was a bit of a loss. So I'm not the expert, but I know a few people in Jive who worked on this, so we can ask them, we'll ask them when I get back how that would work. Because that would be a very logical next step if you want to include this data into the Black Hole Tom instead of having two distinct data streams, one for the VO and one for the Black Hole Tom service. It would be much easier for us to combine that into one thing. But it may require more work on your side to make sure that you talk to the virtual observatories. They are standardized nowadays, but still different from what you do.
We can give it a try.
Yeah.
Okay. And well, I wasn't aware that you were doing microlensing. Long time
It's a
ago.
very, very long distance.
But this is something what I've been always looking into, radio microlensing. This is something, not explored because there are not enough radio sources which can be microlensed. But if there happens to be one, then the milliarc-second resolution you can get, this is going to be huge. So I still wait for a radio source being microlensed.
Yes.
We need
I'm not sure if there's any.
Yeah. The chances are very, very slim. Yeah. Okay. Are there any questions on Zoom? We can't tell. And okay, nothing on Zoom. So I think it's time to stop here. Thank you, Ilse, and thank you for all the speakers this session. And we go for lunch. And let's meet. 2:15.
Can I just say something?
Yeah.
So for this trip, I think the easiest would be for tracking is to I assume you're all on Slack, right? So if you could just write me a message on Slack in the the private chats if you want to go, if you want to, and how many people, if you have +1 or +3.
Do you prefer private message, or should I make like a little comment under which people can sign?
Well,
What do
yeah,
you
maybe
prefer?
this is. I think it would be almost easier if it's private message because of the possibility of having +1 or 2, right? So that I know how many people will be in total. But yeah, so I think this would be the easiest. And then I will book after after the next break. So this.
Simon. Hi, you there?
Hi, Łukasz.
Hi, I'm about to call people in. We're a bit late.
How was lunch?
Very good. You missed very good stuff.
Just don't.
Well, but at least you have coffee. We don't have coffee until the coffee break.
Okay.
Anyway, you can start sharing. You can start sharing your screen, and
yeah,
and I'll start chasing people.
Okay.
Okay, 1, 3, welcome after the break. Hope you have good lunch and good swim, some of you. And we begin the session this afternoon with Simon Hodgkin, who's leading the Gaia Science Alerts. The reason we are here, actually. Simon, the screen is yours.
Hi, thank you. I'm going to test that you can hear me, first of all.
Yes.
Okay, second thing, does my slide change?
Yes.
We have a success. Okay, I'm very happy. Thank you so much for giving me the opportunity to present remotely. I'm really sorry I can't be there with you. I've been able to follow lots of the meeting online. I've been blown away by the results that people are showing. I'm very excited to do that. The long and short of my story is we're running again. So I'm extremely happy to be able to tell you that the alert is live and is now going full speed ahead. So this is the good news. What I will do, I'm not sure who's there and who's not there, and I don't know who's seen this and who hasn't seen it. So I'm going to start off just by giving a run through of the system and how it works, with apologies for those who already have seen this a million times. But I felt that that was the correct thing to do. So most of what I talk about, the methodologies are described in this paper, which is 2021 in ANA, and it's open access, so you can all go and read it. So please have a look and chase me up if there are things that are not clear and you want to talk about in more detail. So the first thing to be clear is that Gaia is, for us, it's a catalog survey. We work with parameterized data. We don't work with image data. So most of the transient surveys do difference imaging, and you can inspect those images and see if a thing is real or bogus. With Gaia, we have essentially point sources detected on the sky. They don't have to be point sources. Some can be extended if they're concentrated enough. And you get lots of artifacts also detected. So here are some pictures of some artifacts from Saturn and Sirius. And what we have to do, and what's done in the initial data treatment, is the picture on the right, where they locate the transients, the measurements, the transits, the per epoch measurements of sources together by coordinates and associate them into sources. So the red dots are Gaia data release 2 sources, and the blue dots are those individual measurements that went in to make them up. So you can see there's quite a lot of scatter between the individual measurements from Gaia. And so we're working with astrometry at that precision, not at the Gaia data release precisions, which are orders of magnitude better than we're working with. We're looking for two classes of event, if you like. We're looking for things that are either completely new to Gaia, so we haven't seen it before, or things that change brightness. And we allow things to get brighter and we allow things to get fainter. And we've seen examples of all of these classes today and yesterday. But in all these cases, we require two fields of view for a detection from Gaia. So we saw that this morning with the symbiotic story. I think we didn't alert on, it didn't have the two fields of view in April, but then we came back to it, it was still bright and we could alert on it with two fields of view. We also require that the event be brighter than 19th magnitude. So that's the threshold that we set so that we don't have too many artifacts, because the sky is full of artifacts for Gaia, unless you do an iterative data processing, which we don't have the luxury to do because we're a real-time processing system. We're not accumulating data and trying to release it on yearly timescales as Gaia data releases. So what we end up with is large numbers of transits. So they're of order 10 to the 8 per day. This is just in one day. And essentially we run mitigation, say, are they good transits? Are they bad transits? Do we trust these data? For the ones that we do trust, then we run detection. So we look for the things that change or are new to Gaia, and then we try and classify them. And classification means basically, is it real or is it an environmental effect? Then we do additional filtering where we look at the environmental effects of the sources, see what's near these sources. And then finally, for a small number, so there's 20 or so per day, we have to eyeball them. And those ones that survive eyeballing, we then publish. Where, oh dear. Okay, the button didn't work. There we go. So this is to try and give you the scaling relationship. My cartoon was a cartoon. So at the top is the data that we're dealing with per day in our database, which is 10 to the 8 or so events, transits per day. And then the fraction of those that actually turn into candidate transient events is the blue wiggly line. So there's of order 1,000 a day. And then after mitigation filtering for mostly environmental effects, then we end up with something like tens per day. And then the final number that we publish is of order 10 per day, which is the black line right at the bottom. The filters that we're running in alert pipe are to get rid of things that are in the wings of a bright star or connected to one of our solar system bodies that may be close to where we're pointing or actually in the field of view sometimes. Or if a star is close to a star, then that can also trigger photometric effects and cause brightening of sources. We also have to classify and reject known variable stars from DR2, now updated to DR3, known solar system objects, and anything that looks very red and has historically high amplitudes and possibly periodic behavior as well. We try and reject those early on so we don't alert on every Maya in the sky. So just to reiterate, this is a catalog-driven survey. We don't have any images from the spacecraft. So what we have to do is use a number of different figures to tell us what we're seeing with Gaia. So we look at the history of the source. So we see its light curve, and there's a brightening event. I hope you can see my mouse. We can see its color historically and actually now. We can look at, oops. We can look at where the transit event, which is a red, compared to previous historic measurements, see if it's offset or it's actually aligned with the previous measurements. We look at the goodness of fit is another parameter that we care about. And that's the shape of the point spread function or the line spread function more commonly for a Gaia source. We have a one-dimensional measurement of its profile, and we see if it looks consistent, stable, and approximately stellar. So these are the kind of parameters that the eyeballers, figures for eyeballers are using to try and decide if this is real or bogus event. And then we also look at association data from Simbad, for example, for pan stars, from images, just to try and get some contextual information as to what this likely likely event is. We also have access to the BPRP spectra, so we can see if there are strong emission lines. We can see if it's intrinsically very red or very blue. So those are the human view of an event, just to show you what the sky looks like to Gaia and to us. So there's a key difference here between discovering something that changed brightness. So this is the light curve of Gaia 16 AYE, and you see it change by about a magnitude. And that was our comment. Red star brightens by a magnitude, or red source brightens by a magnitude. And it's only when you combine it with follow-up data or historic data, some of these red came from Assassin, I think it was, and then this very detailed follow-up that Łukasz and team triggered to, and lots of you were involved in, that you actually really understand the nature of the event. So unless you're doing this detailed photometric follow-up or spectroscopic as required, you won't really understand what the transient sky is doing, what's going on. And so lots of these events that look kind of quite common or garden or boring can turn out to be very exotic and very, very beautiful. The photometry that you get from Gaia, the cadence is so low that you cannot constrain this model from it alone. You needed to have your photometric follow-up to constrain this model very precisely and understand the true nature of this event, but it was a binary lens in this case. Another event that I think is worth mentioning is, because it's close to my heart, this is an FU Orionis outburst that was picked up by Lynn Hillenbrand and her team, which was a Gaia source that brightened by a couple of magnitudes. I think it's 3 magnitude brightening. In 2017, we alerted on it and it continued to rise. And what they did was go back to the WISE satellite and find there was historic data on the same source that showed the brightening happened earlier in WISE, so in the mid-infrared, than it did in the optical, suggesting that the event took place further out in the disk and then moved in over time. And so that was informative and gave us an insight into the physics of FU Orionis events that we hadn't had before. I think it's the first time this had been seen to happen. Another paper that I think is really nice, well, this is from Adam Kawash, who I think is no longer in astronomy. Sadly, he's gone on to do other things, but for his PhD, he tried to work on the galactic nova rate and took estimates by combining Assassin detection of novae with the Gaia detections of novae. And in particular, in 2021, we had the largest number of novae detected ever in the history of the Milky Way, and observations of the Milky Way. And Gaia was one of the contributors to that effort, and in fact detected more novae than the other missions. So it dominated the detection of novae in our galaxy in 2021. So Adam was able to constrain the observational measurements of the number of novae and then compare that to predictions from models, and show there's still this discrepancy that the rates are below the predictions, but his measurements are actually a little bit closer to models than previously seen. And that's largely because Gaia can see into the extincted regions in the plane and found objects that other surveys previously were missing. So this is where we are now. Since restarting, we had this pause from May until we started again in end of August. And so we had this sort of almost 4-month delay while we were refiguring our database. So trying to get things to go faster. We had essentially nearly 9 years of continuous operation with this hiccup. What was happening is our database got so full, so crowded. It wasn't designed to do a 10-year mission. It was designed for a 5-year mission, and with no sort of investment in the hardware or especially the people to continue this. We've been running basically a system that is out of date and needed to be updated. It's still working, but it's very much on a best efforts basis. What we managed to do was try and refactor our database to move half of our data, roughly, into ancient history, we call it, and so that the live working photometry tables are much smaller than they were. And the hope is that this gives us a speed up. We're still testing whether the speed up is really real or is just the part of the scanning law we're on. It's not obviously much quicker. However, for the last month or so, it's been quite stable. And so we're happy, and we hope that it will continue to operate stably. I thought it was going to be sort of a magic solution that would fix everything and be 10 times quicker. That did not happen, but hopefully it's going to be stable enough that the very biggest hill pixels we can live with and we can work with. The other thing during this process is we learned that backups of our system is very important. We completely broke our database trying to make our database better, and we were able to completely rebuild it from our historic backups, and that was a tremendous relief as well. And because otherwise, re-ingesting all of the Gaia data of the whole history of the mission would have been a bit of a nightmare. So what we're producing is precise photometry, where the precision is 1% in the flat part of the curve down here, and about 3% at 19th magnitude. Things that are brighter, essentially there's a bit more scatter in those measurements because the image parameters we get out of the initial data treatment don't handle those quite as well, and so the Gaia data releases are much better. This calibration is a historically calibrated data set, so we're always predicting what the calibration should look like in the future. It's updated in theory almost monthly. In practice, it depends where we are, where CU5 are in the processing cycle as to whether they can do it as frequently as that. For now, we haven't had an update in our calibration for a little while. The Gaia is so stable that we can get away with it. And the astrometry is, I showed you the horror plot of the big scatter between the different transits, but if you look at the scale of those figures, then what we see is our error, our standard error on a single photometric measurement is about 55 milliarc seconds, which is incredibly good, which means that essentially if we detect a supernova or any class of transient event, ours will be the best astrometric solution available. Some of them do make it into Gaia data releases, and then the astrometry gets better again. But essentially, at the point of our publication, we are the ground truth for transient surveys for astrometry, if we've seen it. And just a few words on classification. So 28% of our alerts so far have been classified. And by that, I mean spectroscopically or unambiguously in the case of microlensing events, it usually involves a model fit and a spectroscopic classification. And these classifications do come from other people's follow-ups, and they tend to be published in the case of supernovae through the Transient Name Server or through astronomical telegrams. And they also come through Simbad eventually. Supernovae dominate the classification. That's this much larger than half fraction here, but that's the bias in the follow-up. So lots of people want to follow up supernovae and go and chase them, and they have surveys ongoing specifically to that purpose. Other classes of events, people aren't so there isn't such a scientific urgency, I suppose, for those classes of events. So what it does mean is we can't extend this classification of 60% being supernovae is not representative of what the underlying distribution are of the 72% that we don't classify. And one way to see that is that Gaia is an all-sky survey, whereas most of the other surveys, apart from the Saturn, are not. They have big gaps in the galactic plane. And so if we look at the distribution of classified sources, then we see there's a hole in the middle, and distribution of unclassified sources really dominate the plane. So a lot of the unclassified events that we're triggering on are associated with the plane, and therefore are galactic in origin rather than extragalactic in origin. And it's illustrative to look at, we do have information. So we have BPRP colors as well as parallaxes from Gaia data releases and G-band photometry. So in a figure like this, you can look at the evolution of a few different classes of events to show you what you could, in theory, do if you took our spectra, integrated the fluxes, applied a naive calibration, and then try and tell the difference. And arguably, you can do a good job of telling the difference between X-ray binaries, novae, symbiotic stars, YSOs, and CVs. And so we did try and do that in our paper, and this was work led by Thomas Cuevas, who I think is going to talk to you later. And he showed that you can do a nice classification exercise between young stars and CVs using a training set of classified young stars and CVs, which works pretty well. And I think we had a 600 odd new CVs classified, and then others doing and extending this work. And you had a talk by Enrique Solano yesterday talking about classification using the virtual observatory. And this is work by Mystery in 2022, where there's almost 3,000 new candidate CVs from our alert stream. And so that's using the parallaxes where they're available. And this classifier went a bit further because they included AGNs, QSOs, as well as supernovae, as well as CVs. So they had a broader range of classes that they included. A few words on Gaia X, because I'll have time. So we've been running this since March 2021. And it's alive again. So we started it, and now it's really live, whereas before it was run sort of just in the test phase. But now it's since we came back, this has been fully open to the public. And this is of interest of those who are looking at simultaneity between different transient surveys in time, space. So all of our events, you can check the timestamps, they're incredibly precise, and see if we have a measurement of something you have a measurement of, or somebody else has a measurement of. And so that sort of combining these data will give us a lot more information input and improved astrometry. We only require a single field of view. We go all the way down to 20.6 magnitude, so much closer to the Gaia detection threshold. We do apply some filtering, so in the most dense, crowded regions of the sky, we have too many false alarms, so we've excluded those. And we tell you the name, we give it a source ID, the time, RADEC, and some photometric parameters for all those events. And the hope here is that we will one day, if we're lucky, have an overlap with one of the gravitational wave events. So I'm going to finish up with 2 slides. So looking ahead, we've finished refactoring our database. We think we may see speed ups, but they're minor. They're not as significant as I'd have hoped for. To this day, I find that databases are incredibly powerful, but incredibly hard to understand when they get to the several hundred terabytes volume level. With a non-distributed database and as Postgres with a fairly old version, there may be things that if we had resources or if we had improved hardware, we could have done better, but we made the best of it and it's still working. Gaia X is live, and that's Susanna's paper out in 2020 describing what we're doing, and a recent paper out this year, it came out in August this year, by Sumedha Biswas, is testing what happens if you look from the ground at the same events, same piece of sky that Gaia's looking at, and look at the things that there are seen in common versus those which are spurious, either from the ground or from Gaia. So there's analysis of that. We may start running in a fully automated mode now that we're back up and running again. The trouble is we need to retrain our data set with this new version of our tables. The idea would be to replace the human eyeballing of all the figures I showed you with PyTorch, essentially a machine learning algorithms, random forest as well for the data, to try and come up with the same answers. So to be as reliable as humans, that ought to work. It seemed to work very well in practice, in principle, and on the tests we did. But we need to retrain that machine. And again, this is a resource problem. But I hope we can do that soon. We have extended our hardware support for the remaining 1.5 years, and we are looking at whether we can port the software to a different hardware system now, which is a high-performance computing Iris system here in Cambridge. So work's ongoing to see if we can do that. Again, subject to having the resource, the humans who have the time to do that. But our commitment, our goal, at least, is to keep running Gaia Science Alerts until the end of the mission, 2025 Q2. So that's 1.5 years away. And so we plan to keep generating alerts until then. And for a summary, I'm really impressed with the amazing science that you are all doing with the alerts we're publishing. It's really wants me to keep this running, even though it's quite hard and stressful sometimes, but I really hope that you will keep doing amazing science, which is well beyond anything we imagine. Lots of the things you're doing is incredible. The details, a lot of alert, 23,000 accurate, precise astrometry, one of the few transient surveys that do the plane, which leaves us open to finding discoveries that a lot of other surveys miss. There's plenty more to do with classification of the alerts that we're publishing. And machine learning is showing us the way that you can do a pretty reliable classification of our alerts to allow probabilistic population breakdowns. And Gaia X does give us a chance of seeing something detected by gravitational wave experiments. So I hope we'll see that. And I thank you for your time and your attention.
Thank you. Thank you, Simon. Questions, comments, Simon? The end of the mission you mentioned is actually, I think it's February 2025. It's not so optimistic as you said.
Yeah, I copied Q2 2025 down from a website at some point. Maybe it's Q1 now.
Yeah, I'm afraid it is so. But anyway, it's good to know that we will be running until the very end, to the last point.
That's the goal.
Let's go. Okay, I don't see questions, comments here. People are still digesting lunch, but thank you, Simon, for this. And let's move on.
Okay, thanks very much.
And screen back. There's a question from Siegfried. Sorry, I didn't see that. Siegfried.
I had a small question about, can you give some details about your machine learning capabilities? These are based on neural nets, I assume?
Which one, Siegfried? We run two. One is for classification publication of events, and the other is post-publication, trying to classify what they really were.
Okay.
So the trying to decide whether or not to publish is we use PyTorch and Random Forest, and this was built by Gabor Kovac in Concordia Observatory, and that we are showing it the same data as the humans, and just saying we show it pictures and we show it features from the light curves as well for the Random Forest, and say, do you agree with the humans? It's trained on the humans, and essentially, you wouldn't be surprised here, it does what the humans would do 99% of the time. So it's like remarkable.
Very good.
Yeah, it's very good.
Okay, good. Thank you. What is that? What does it say? Oh, and then what?
Siegfried wants to record it on his computer.
Siegfried, we have everything recorded, so I will not let you. Maybe you pressed the wrong button. Anyway, let's move on to the next talk. Edyta, are you with us?
Yes, I'm here.
Okay, so you're on the big screen now. If you could start sharing.
Yes, I'm starting. Okay, can you see my screen?
Your screen, yes, but not in the presentation mode yet.
Yeah. Okay.
That looks good. Okay, the screen is yours.
Okay, thank you. I'm really sorry that I can't be there with you. And now I'm sorry even more when I saw the nice photos taken by Milena. But anyway, today I'd like to tell you a few words about the Gaia ground-based observational service for asteroids, which is a service created for asteroid observations and a service created to facilitate collaboration between professionals and amateurs. People can use the Gaia GoChile in a few different ways. First of all, they can support the Gaia mission taking ground-based observations because Gaia provides us only spares in time points for asteroids, and from the ground we can cover the whole rotation period with many points, so we can combine the data, getting more results. So usually the people are sending us the raw data, and we do the whole procedure, the reduction and photometry, and of course show the results to the observers. But the data are used for further analysis. And observers can also do the asteroid occultation records, which helps to determine the real size expressed in kilometers and the approximate shape of asteroids. So far we've got over 180 registered users, who send us more than 1,000 nights of observations. And there are some papers published in Astronomy and Astrophysics, Nature Astronomy, and monthly notices, and so on. So here at the left, you can see top 10 observers. The most active, Joseph Bosch from Spain, has observed more than 260 nights and sent us the fantastic data for asteroids. And when you go to the Gaia GoChile, you see the main screen with a list of asteroids for which we need observations. And here are the most basic informations, like how many light curves, how many percentage of light curves do we have already covered, how long the object is going to be visible, and what's the magnitude range till the end of the visibility. And if you go into details, you can see even at what time, the specific day, the observations should be taken in order to cover the missing parts. So the easiest way of using Gaia GoChile is to go to the planner. You can specify your location, range of magnitudes in which you are able to observe, and you will see the list of objects visible from your side. If you choose one or few objects that you want to observe, you will create the detailed observational plan with many informations like radius extension, declination, elevation, and azimuth for maximal elevation, and when the time of the start and end of the visibility of the object. And all of these informations, you can even you can go even to more detail plan and see how the asteroid is moving in the background of the sky field. So you are getting all necessary informations to perform observations. And Gaia GoChile was built to support the Gaia mission. That's why, thanks to our colleagues involved in the mission, we've got predictions, and we can see which objects were observed, are observed at the moment, and which objects are going to be observed in the near future. In this way, you can plan your observations and take your measurements at the same time as Gaia is observing the particular object. And one of the main things that we are doing is at the bottom left picture, you can see the example of the light curve that we can have from the ground. And on the right panel, you can see the Gaia measurement with fitted ground base measurement. In this way, we have, let's say, absolute measurements which can give us more information and which allow us to obtain more accurate physical properties for asteroids. So this is my last slide, only with the address of the service. So please go there, see what's there, and enjoy. Thank you.
Thank you, Edyta. Indeed, this is a very useful service, and it kind of overlaps with our activities because some of our telescopes are actually participating in both of these programs. And I, of course, encourage people who are not doing this yet to join this, and vice versa. I hope some of your telescopes will also be happy to join our network. So we should look for some overlapping activities. Questions, comments to Edyta? There is none. Come forward. Now you have to come forward.
Do you also do the cross match or with Atlas?
Łukasz, could you repeat closer to microphone?
Oh, sorry. Yeah. Do you also do cross match with Atlas?
Yeah, we were trying to do it, but there are differences depending on the filters and accuracy. So at the beginning, at the moment, we rather go to the only Gaia data. Maybe at the later stages we will compare the data also with Atlas, but at the moment we are using only the data from the Gaia.
Okay. I was just wondering.
That's a very good point, yeah.
Yeah.
Okay, thank you, Edyta. I'll take over the screen from you. We have a slight change in the schedule. Nothing to worry about too much, except that Michał has to speak earlier than he was promised to. So I'll make this. I hope it is okay. Okay, Michał, here's the mic, and here is the controller. There you go.
This one?
You know the telescope.
My name is Michał Zajmo. I'm from University of Zielona Góra, and I'm going to talk about the ROAD telescope, our robotic optical telescope, University of Zielona Góra. And I have to say at the beginning that the name was invented by Agnieszka Słoikowska. I don't know if Agnieszka is, I'm not sure if Agnieszka is with us here, but thank you, Agnieszka. Yeah. Okay, you can see this is a nice photo of our telescope in Chile, because we spent the first year in Spain to test the system, and then after 1 year in Spain, we moved to the Chile. And now I'm going to talk about the results after this first year in Chile. Okay, third question, where is Zielona Góra? Zielona Góra is somewhere between Poznań, Berlin, and Wrocław. We have a small institute there, but mostly with radio astronomers, and I'm the only guy who works with the optical data. Now there is another new astronomer that is working with the infrared also. And okay, about the ROAD specification, this is not real photo, but our system looks really similar. That we have the two telescopes on one mount, And the main telescope is 0.5 meter corrected dark Kirchhoff with the QHY CMOS camera, and the second telescope is 0.25 meter RASA telescope, Roe Ackermann something astrograph. I don't remember the name. Also with CMOS camera, almost the same, but with the bigger chip. And there is also no filter wheel on the second telescope. The main telescope has a filter wheel with rotator and motofocuser, of course, and everything is on the L500 mode in ALTAS mode. Then very nice things about this mode is that it's direct drive. There is no periodic error. The pointing is better than better than 3 arc seconds, and the slew speed is up to 50 degrees per second. I mean, you can move from one side of the sky to another in 3 seconds with very high precision. This is really amazing, amazing thing. Yeah, and there was a discussion about the CMOS before, and I add some. I would like to add some few words to this discussion. We are switched from CCD, Moravian CCD, to QHY CMOS. Disclaimer: I have no connection with the QHY company, of course, but we are using this camera from QHY because the price, and the specifications. The CMOS are really cheap. The camera that we are using with the main telescope is around 4.5 thousand euro, and as you can see, there is very high quantum efficiency. 91% is pretty fast. Moravian with the full frame readout time is about 11 seconds. Here we have a 3.3 frames per second with full frame, which is amazing. We have a pro version of this camera. It means we can connect the camera not only with the USB, but we can use also the optical fibers, and then we can reach even 20 frames per second with the, for example, 12 bits or something like that. Yeah, it's really fast. And in our Pro version camera, we have the GPIO port that we can use for GPS injection. We can connect the GPS to this port to trigger the exposure with the GPS very precise time, because the exposure is triggered by the GPS. Yeah? And this is a very important thing. With the CMOS camera, you can use the multiple readout modes. And here you can see the example of the curves of this mode. And for example, if you want to use, I don't know, if we need the very depth full well, we can choose the extended full well mode with a little higher readout noise, but with very depth full well. Okay, but if you want to observe the faint object with the high time resolution, you can switch to the high gain mode with some gain, for example, 56, to reduce readout noise. You can see the readout noise is here on this high gain mode. Is much smaller than in this full well, extended full well mode. But of course, with reducing the readout noise, you also reduce the full well. But if you want to observe the faint object, you don't need to use the very big full well. Yeah, and yeah, this is the very nice things that you can do with this camera. This is an example from today morning. The same object, the same exposure time around the brightness of this object is around 50.7 magnitude. The same exposure time, 10 seconds, full well mode, and signal to noise 28, high gain mode, signal to noise 44. The same exposure time, but the different mode camera, it's clearly visible that on the high gain mode, the signal is much better. Okay, here is an example of the light curve of the object. The first part of the light curve was taken with the full well mode, and the second part, you can see the gap here. When I change the mode, this is with the high gain mode, and yeah, 15.7 Gmac, a very fast cataclysmic binary, and you can see the difference in the error between the modes. This light curve is without any bias and any dark. This was totally raw data. Okay, and about the place, our telescope is located in the Deep Sky Chile telescope hosting, the south on the Atacama Desert. You can see here is the Deep Sky Chile, and here is the Gemini South. We can see on the horizon the LSST, which means we are very close and in very nice place. Our telescope is in one of the shared observatory with the automatic roof. Nothing special, but it's okay. Okay, and our telescope is fully robotic, but it's nice to have some way to check if everything is okay. And for that, we created this website. It's open. It's open website without any password. Anyone can check the camera, the all-sky camera from the telescope, general all-sky camera from observatory, and some basic data about the weather and so on, which is really nice. And the nice thing is that the night, now the end of the night is around 11 a.m. It means you can observe or you can check something, or you can observe with the students, for example, the morning, yeah? Which is really nice. Okay, and our control system, we are using the Abbott astronomical robot system created by Sibilla Technologies, the Polish space industry company. This system allows us to plan observation for the next days, takes care of the observations and calibration of the data. Only what we have to do is to make a plan for the next, I don't know, few days, 1 week, 2 weeks, or something like that, and then we can download every night we can download the reduced data with astrometric solutions from the FTP server. There is no more romantic astronomy. Totally. This is how it looks. The scheduler, the web plan, as you can see, is the plan for whole week. This green lines marks the BH-TOM observations, but also after the first round of the planning, we have always some gaps, and for filling these gaps, we need some kind of API. For example, I saw in the BH-TOM 2 there is API, because in the second round of the planning, if there are some gaps, we are just asking some APIs if there is any object that we can put to this gap and then add this to our scheduler. And main objectives. One of the main objectives of our telescope is the exoplanet's transit timing. And the ExoClock project aims at monitoring the times of exoplanetary transit for Ariel, future Ariel mission, and we are also in the test mission follow-up in the Seeing Limited Photometric group in cooperation with the Rozhen Observatory. And I want to, okay, here you can see some results from our ExoClock observations. This is about if there is a possibility to make a precision photometry with the CMOS cameras. And as you can see, here we have some confirmed transits. And please note the depth of this transit. This is about the 6.5 millimagnitudes. And even we have the confirmed transits with the depth 3.3 millimagnitudes, which is really good. And there is still plenty room for improvement, because we can, for example, reduce focus. I mean, to use some defocusing to increase exposure time, to collect more light, and to get better data with smaller scatter. Yeah? And yeah, here you can see the example of the O-C for this LAS object. And this is interesting thing, because ExoClock, on the ExoClock website, this object was proposed for the telescope with the minimum aperture of 40-inch. Our telescope is 20. Yeah. And there is another example of the observations. Photometry and data reduce was made by Olga Michniewicz. She's a high school student from Zielona Góra, and it is really nice that even high school students can learn how to reduce data, can upload data to the ExoClock. And yeah, here you can see some details about this object. The depth is 11 millimagnitudes, which is really also really good result. Yeah, and the point is exactly in the center on the zero line on the O-C for this exoplanet. Okay. Another example, another main objective is asteroid observations for Anna Marciniak from Adam Mickiewicz University in Poznań. Here you can see the example light curve. Here is the animation of the planetoid, and here you can see all of these blue and yellow points were taken with our telescope. Also, because there is an astronomer in our institute that is working with the infrared data. Our telescope is not infrared telescope, but we have we made some observations of the brown dwarf. As you can see, there is a possibility to make observations with the good photometry precision of the small sample of the brown dwarfs, and probably next year we'll have the special I-band filter for ultra cool dwarfs, also to improve the quality of the data. And we want to monitor this. We want to make a long-term monitoring of these brown dwarfs objects. Okay, of course, the BH-TOM is also one of our main objectives, and we found the BH-TOM as a great tool for long-term monitoring. Here you can see the light curves from quasars that we add to the BH-TOM. I don't remember the name of these quasars, and this is one idea. Maybe it would be good to add the name of the plots, the name of the object to the plots on BH-TOM. Then it will be easy to copy the image.
I will break you here. So the visual list, if you make the visual list, it has the name on it. And the purpose of the visual list is actually you copy paste it into the papers. Also, it doesn't have the background, which, for example, some journals don't approve. So you can take the visual list image of your object and then copy paste it into a paper. And it has all the labels and it has the name of it.
Okay, yep. But yes, we are using the BH-TOM to collect our data, to make a photometry of the quasars, which is really, really nice. And some ideas to make a possibility to delete data from the team. For example, as you can see, there are some bad data, and there is I can delete them because they were updated with the Olga, I think, with the Olga. And the idea is to add the expiry date for an object, to remove all of these objects from the top of a list with the zero number of observations. Yeah. Now this is the screenshot from, I don't know, yesterday, I think. and 1, 2, 3, 4, 5, first 6 objects are with a high priority, but without any observations, probably not valid. And it will be nice to add some share link to plots, to share plots without account. I mean, to make the plots visible for the people without account, maybe.
You can download PNG.
I have to download and send this plot every week, for example. Okay, but anyway, today morning, very fresh observations about Gaia 21 FKL, which already I upload them to the VHTOM 2, and it looks looks fine. Come on, almost. But you can see observations from today morning from 8:20. Everything looks pretty good. And also, please note that there is a point from this morning with the magnitude 17.5 with very small error, which means our observations are very, very good quality. The
pipeline is so good.
Yeah, maybe there is somewhere divide by 10, something like that. Yeah. Okay, another main objective of our telescope, the SST near Earth object tracking. Here you can see the re-entry of the satellite Olius. I'm not sure about to pronounce it correctly, but as you can see, this is the altitude of 260 kilometers, which means the object was pretty fast, and we are able to observe it and tracking it with the high precision, as you can see. Yeah, we catch this satellite somewhere here. Yeah, in this moment. And another nice, the Indian satellites in the way to the moon, which was a really break news in the Indian news. Even in the television, they said that our satellite was captured with the Polish telescope. Really, this was really big news in the news. And here is a yeah. There was also of course an error because they say that the telescope in Poland. Yeah?
That would be something, right?
Yeah.
That would be
but this is about our telescope. We also cooperate with a small telescope net. With the telescope in Spain, in Turkey, in RS Observatory and Piwnice also. And yeah, join us if you have any project and would like to use our telescope. Contact us, and also we are looking for new employees in our university. If you want to join us, just contact with our director or me, for example, and because we are looking the new astronomers that can work with our optical data. And thanks for your attention.
Thank you. Questions, comments, Michał?
Is this software from Sibilla suitable for longer runs? For example, if you want to observe one object for the whole night with multiple filters, or you have to prepare it in this 15 minutes beams?
Yes, we can observe one object whole night with the different filters, different exposure time, or something like that. But we are using the 15-minute slots. Yes.
So the one slot has to point again after the.
No. But you can change the object. Generally, the system is built on this 15-minute slot, but you can include many objects in one 15-minute slot. Yeah.
So I have two questions. First one about the animation you show. What kind of FPS does have to be applied in the camera in order to track, because you are tracking the object using the fast imaging, yes?
Yeah, and I don't know what was exactly the FPS. One thing, these images were taken with this RASA telescope, because this RASA telescope has a very wide field of view, 3 by 2 degrees, which is very, very big, yeah?
And the second question is, you said you are going to have a new filter, yes, for the brown dwarfs?
Yeah.
Well, what about the more bluer ones, like near UV? How high is what is the altitude of the place?
1,705.
So your telescope would be ideal for every night monitoring of open clusters. Only in EU band. That would be ideal. 20-30 minutes of observations each night.
I'm not sure about the UV because I'm not sure about if
your camera is
not camera even, because there is a corrector in the Dalkircham, and I'm not sure about the
so it would probably the wavelength would be shifted in a way. Okay, thank you.
Yeah, I just wanted to add that with PlaneWave you don't need to track on this target. You can, for example, give orbital elements.
Yeah, of course. Here, yes, this is how it's done. Yeah, you can use these 2 line elements, yeah, for the tracking of the satellites or new objects.
Yeah, I wanted to ask you about the schedule you showed. So it means that you can enter something in your queue like manually, right?
Of course.
So
yeah, of course.
Okay. But then also you're looking for kind of filling the gaps automatically, right?
The first round is done by automatic way, and then the second round now is I'm making manually filling the gap now. But I want to switch to the second round. If there is any gap, then just check in the APIs or something like that to fill these gaps with the additional objects. Yeah?
So I think this is something what we could see while we are here, actually, to define the API most suitable. Actually, you don't need to worry. You show these high priority targets which are sitting there. But if you apply some very simple filtering, you get rid of these kind of spurious ones, which kind of sit there. I fully agree that an idea for expiry date is a good one. But with some simple filtering, you can get rid of these very quickly and then fill with a couple of them.
But of course, it will be much easier with API.
Yeah.
Even
so
if I need to run my script manually to check the list of the objects and then
that's what I mean. The filtering is in API as well.
API,
so you can define your filter once and for good.
Perfect.
And then run it and give me the list of targets which satisfy my criteria.
Of course.
That's what you need. Right?
Yes, exactly.
So then we can sit while here today or tomorrow and do it actually.
Okay.
Thanks. Good. Thank you, Michał. Let's move on. Now we have Siegfried.
Łukasz, your thumb says his hands.
Let me just make the screen for you. Josh has a question.
Yes, a question from Josh.
Josh. Yeah, I mean, I was very much surprised about the differences in the modes. I mean, I'm using a QHY 600M as well in Chile and here in Belgium. I have sent to you via the Black Hole Tom Slack a request that you share your email address with me so that we can discuss differences in the modes. I was really surprised that the high gain mode gives you even higher higher efficiency of the QHY camera.
Okay, I don't think he got the question, but Michał, there was a question to you, but there is a Slack message. Sorry, there is a Slack message from Josh to you.
Okay.
Okay.
I also had a question.
Okay, guys, let's move on. So, Siegfried, if you could share your screen, I'll put it on the big one.
The screen. You should see PowerPoint now.
No, we don't see your screen yet. You're not sharing. Okay.
No one sharing. Okay.
We see your screen. Yes.
Okay.
Not your slide. Okay, that's better.
And now it should be there.
Yes. Yeah. So the screen is yours, please.
So I all have been invited by Łukasz to give a short overview about recent developments on the Gaia Alerts program at Astrolab RS Observatory in Wipers, Belgium. So I will provide a few details about the history of our observatory. Astrolab RS Observatory is located near Wipers, the famous city in the western part of Flanders in Belgium. And it is a public observatory with funding from the Flemish government. It grew out of the local astronomy club in the course of the 1990s, and about 10 years ago, it became a public observatory with funding from the Flemish government, which is involved in many educational and popular scientific activities. Over the course of the years, our team members have been active in developing new telescopes and instrumentation. And this project culminated in the development of the 68 centimeter telescope, which we call the new multi-purpose telescope, and MPT, which is shown on the picture. And we have been using mainly for photometric research over the last years. This has resulted in many science publications already. In 2014, we established a local research team with 4 members. From left to right on the screen, Ludwig Logis, Steve Rauw, myself, and Frankie Dubois, which are operating this telescope, and of which I am mainly the academic member. Then a few years ago, we came in touch with Łukasz Wizikowski, and we became members of the Gaia Alerts program. And we began submitting data of observations of microlensing events to the black hole TOM. Over the course of the years, this has resulted in several new science publications, which are in preparation now. One of which is a paper on the galactic microlensing event Gaia 19 DKE, which is led by Marius Mascoliunas of the University of Vilnius. This is an important microlensing event because it is long duration, and it on the photometric data you can clearly see the effect of the annual parallax on the photometric light curve. This event has been analyzed in detail by Mascoliunas, the lead author of the paper. And the important part is that the result is that the lens in this case must be a compact object, most likely a white dwarf with a mass of about half the mass of the Sun. So this is an interesting result. There is also a second paper in preparation on an other microlensing event, Gaia 21 DNC, to which we also computed data from Astrolab. This is important because this is a planetary microlensing event in which the lens is a double lens consistent with a planetary system in which the host star is a M dwarf, and the companion of the host star, so the second component of the lens, is a exoplanet of Jovian type. This paper has been submitted to Astronomy and Astrophysics and is now under review, and the analysis is now focusing on determining better properties of the source to pin down the solution better. Over the course of the last years, our team member Frankie Dubois has been developing a new home-based observatory at his home in Langenbach, which he called Adonis. It is equipped with a 25 centimeter London telescope of the Skywatcher Quattro type, a popular Chinese design, with a Moravian CCD camera with a full set of photometric filters BVRI. This telescope has been used to submit already hundreds of images to Black Hole Tom. Frankie has been instrumental in uploading images and helping to debug Black Hole Tom, by the way. An example of which is a new microlensing event, Gaia 23BAY, which appeared as a Gaia alert at the start of this year, and which we observed from Langenbach over the course of the last months, resulting in a very good light curve. The observatory is about to be expanded with a second telescope of the same type, but this telescope will be optimized to be controlled remotely from his home. And so we will be able to observe more targets in this way, and also, because the telescope is remote, we hope to be able to do time series photometry on many targets over the course of whole observing nights if the weather allows. This new capability will be useful to potentially detect anomalies in microlensing events if in the future we will be able to have a new alert system that is optimized to do so. And with these concluding remarks, I return my screen back to Łukasz.
Okay, thank you very much, Siegfried.
Yes.
This is a very nice example of
yes,
collaboration and with enthusiasts who are equipped with good equipment, right? Any questions, comments, Siegfried? What is your magnitude range with the telescopes?
With the current telescope, we go to about magnitude 17 as the limit, we think.
17. Okay.
Yeah.
Right. And the cadence of observations is how busy your schedule is, how frequent you can observe.
Oh, we can easily go to one observation every 30 seconds.
Okay.
On some microlensing events and other Lyrae stars, for example.
Mm-hmm. Yeah, we should.
And so this would be very good if you have anomalies in microlensing events and we have new alert systems.
Mm. Well, the thing is that you can only find the anomalies if you observe the alerts, the microlensing events very frequently. So yes, you can find the anomaly on the events we find. So it's all up to you.
Yeah, it's going from both sides, in fact, because you also have to share the information quickly.
That's right.
And process the information quickly.
Okay. Thank you very much, Siegfried.
Okay.
Thank you. And now let's move on to another talk, which is almost there. Just give me a second. Justyna Olszewska is going to give us an overview, quick overview. Quick. There you go. Yes. And use the mic, yes.
Hello everyone, my name is Justyna Olszewska. I am from Astronomical Observatory Institute Adam Mickiewicz University in Poznań, and so normally I'm working with SEP8, and here I'm gonna talk a little bit about observation, which I have this year. So one of my dreams was to be an observer in our university, and thanks to the SARA consortium and the Institute Astronomical the Canarias, I can be an observer this year. So here we have 5 telescopes where I am observing. The most important is RPT because it's our telescope from our institute, and of course we have the 100% time. So here you have some details about the telescope on the left, and on the right is a list of objects which I have observed from the BH dome, and I can still have like 30 or something like this nights. So we can still work together. And but main goal of my observation is to make photometric observation of the eclipsing binaries asteroids. So here you have so these are very interesting and unique objects, and we only know a dozen of them in our solar system. So the main thing about it is that because of period, single observation must be at least something like 3 hours. But if I am observing, for example, 2 asteroids, I always have something like 2 or 3 hours to make Gaia alerts. So here you have 3 of light curves, depending of how it looks eclipsing. And in the end, I want to just show you how we are working with such light curves and make models like this. Thank you.
Okay. Thank you for that. Quick questions, comments? I have a question.
I know that Łukasz have a question.
No, I don't.
No?
So are you planning to expand the network of the telescopes? Because there are several telescopes. Maybe we can add someone.
Okay, maybe we can.
Are you planning on doing this? Because your telescopes are located in these particular locations, but you could have one, let's say, on the in Australia, to better cover the.
I guess in your case, it's necessary to have continuous coverage, right? Or you can propose your targets to our network.
Of course, okay.
Okay.
Yeah.
Good. That's very exciting, and it's quite an interesting and challenging, on the other hand, scientific avenue, which we haven't undertaken in our system because your targets are running away.
Yeah.
So
we can cooperate.
Siegfried, yes, please.
Yes, I have a question. Did you also observe Didymos, the asteroid redirection test from NASA?
So, no, not me, but somebody from our institute, I think so.
Okay.
Good.
Something about.
Good. Thank you very much, Kristina. Just a very quick one because we have to move on.
Is this kind of work also included in asteroid Josch, the Gaia Josch website?
Seriously?
As alerts, for example, or?
I don't know. I can just ask because normally I'm working with stars and here I only observe. So
yeah.
But I will ask.
I would be interested.
Okay. That's fine.
Okay. Thank you. Let's move on to the very last talk of this session. Jamal Hamed, are you there?
Yes, I'm here.
So the screen is yours. Go ahead and share.
Can you see my screen now?
Yeah, we do. Okay.
Good afternoon, everyone. My name is Gamal Hamid. I am from the National Research Institute of Astronomy and Geophysics in Egypt. I work at the astronomy department, and today I'm going to talk a little bit about some follow-up observations of classical novae, and I have observed using our Cataclysmic Astronomical Observatory. Spectroscopic observations. We have a recently installed faint object spectropolarimeter, and I have used it to do some follow-up observations of one of the more interesting classical novae that has been observed in the recent years, which is Nova Cassiopeia 2021, which has been detected by Gaia as Gaia 21 BPE. I have made some follow-up observations for this object using the Cataclysmic Observatory, and also I have used spectroscopic observations from RTT 150 in Turkey. This was the first object that I have been used that I have observed from Khatameh Observatory from the Gaia Alerts, but I have also, after that, I have observed other cataclysmic variables that have been detected by Gaia. But I have also added our telescope, our Khatameh telescope, to the BHTOM network. But so far I haven't uploaded any data on the network. But I plan to do in there very soon. Let me first talk about a little bit about our telescope, which is the Khatameh Astronomical Observatory. We have a 1.8 meter telescope located about 60 kilometers north of Cairo, here in Egypt. It has been operating for about 60 years now, but recently the light pollution started to grow closer to the observatory. But until now, we are capable of doing nice observations from the location. And we are planning to continue the follow-up observations for the Gaia Alerts. Speaking about the spectroscope observations of the nova, it has been detected in March 2021, and it is still bright so far. Its magnitude now is about the Gaia magnitude is about 12.8. And the detection magnitude in 2021, it was about 7.8 magnitude. I have made several observations using Khatameh Observatory and using RTT. First, let me speak about the Khatameh observation, because they were made more. I have made more observations using it, and as you can see, it was in an earlier stage. They were in 2021, about 6 months after the outburst. You can see multiple hydrogen lines and helium, and some it has started to enter, also show some iron lines and oxygen. It has developed through, I have made observations about in November, then in December, and then in the following year in September. And as you can see that many of it has transitioned into the pre-nebular phase, and also close to the date of these observations, I have made also some observations using the RTT 150 telescope in Turkey through my collaboration with Dr. Hasan Esenoglu from Istanbul University. And we have made some observations. As you can see, there are iron, helium line, and helium lines, and oxygen, and as well as the very strong H alpha and Balmer series in general, Balmer series as lines. And also I have made some preliminary results about the flux and the evolution of the flux of some of the prominent Balmer series lines like H alpha, beta, and gamma, and delta. And you can see them in this table. And we are continuing the observations for this interesting object, and we have planned observations for tomorrow, and we plan to take more spectra, higher resolution spectra for this object, and continue our study for it. And thank you for your attention.
Thank you very much. Are there any quick questions or comments? This is all very nice. I'm very pleased to hear that your telescope is already in our system, so we will definitely be in touch in terms of targets to follow up.
Yes. Cool. We are open to any collaboration projects, and that's why we have added our telescope to your system, so that we can have a chance to contribute to your.
Excellent. Okay, thank you, Kamal. So that will be almost all before the coffee break. There is some fun stuff going around which I'm not aware of, but Milena was going to announce something very quickly.
So I already posted it on Slack, but for those of you who would like to, in-person participants would like to enjoy some nice experience in Valletta, there is a highly recommended concert in the St. John's Co-Cathedral that is happening tonight at 6:30. So the entrance costs 25 euros, but entrance just to the cathedral is 15 euros. So the concert itself, for those of you who like music and would like to visit the cathedral, it pays off, I believe. The concert starts at 6:30. We will go. I mean, at least some people want to go, so we could make a group. Yeah, thank you.
Okay, enjoy the coffee break, and we're back 4:15.
Sorry, I have to.
Możesz zawołać? Hello, hello. Stefan, are you there?
Hello?
Hi, Lukasz.
Hi.
Hi, Stefan.
How are you?
Fine. Well, we're sorry you're not here.
Okay, I will share my screen.
Please.
Oh, okay, alors, 1 second.
Yeah, we do see it.
On here, it's fine.
It looks good. I make it a big screen. Okay, let's begin after this coffee break. Now we have a series of very exciting remote talks. So I hope they will keep you awake because the topics are really very exciting. And we start with Stefan Stefanov, who was supposed to be here, and we're very sorry he couldn't make it. But he's going to tell us about the SFOM mission. Stefan.
Okay, I'm starting. I will give you the latest news of the Sino-French SFOM mission, and also of Colibri. It's a robotic telescope. The main scientific motivation of SFOM, just to remind you, is really to detect and to study the gamma burst. We're highly motivated by this object. Just to remind you, but I'm sure you are completely convinced by this object, but gamma burst are the most luminous source in the universe. And we want to use the gamma burst to understand the phenomena taking place in extreme conditions, of course, to understand the physics of the gamma burst, and to study really the early universe. I don't want to go in much details. I'm here to give you the latest news of the satellite and all the rest. Here, this is a concept of the SFOM. So it's a mission which is shared between France and China. We started, in fact, almost 20 years ago. The space projects are very long, very difficult, very painful. So here's a description of the payload. So we have 4 instruments on board. I will give you much more details, but we have first Eclair, which is used to provide the trigger. It's a coded mask instrument. We have also, it's a large field of view. I will give you the numbers in a few seconds. We have the GRM gamma ray monitor developed in China. And then we have 2 now field of view instruments, one operating in X-ray, the MXT, and the second one in the visible domain. Something also which is very important, we have a set of ground facilities. So we have the Chinese Ground Follow-up Telescope, CGFT. This is it's not very romantic, but this is official name. We have a much better name for the French Ground Follow-up Telescope, which is Colibri. I will give you much more details. In fact, the observing strategy, and I will explain to you, is very similar to the one used by Swift. In fact, you have no choice, and you don't know where the gamma burst will appear in the sky, so you have to monitor a large field of view. And when you have your trigger, you have to slow automatically in this position and to observe this position with now field of view instrument. I can give you much details. So on Eclair, so it's a coded mask instrument, very similar to the one used by Integral and Sigma. Sigma is 30 or 40 years ago. It's very old facility. The field of view is about 2 steradian. It's not a flat sensitivity. We have a kind of top hat, something like that. Something interesting that the energy range covers between 4 keV and 150 keV. 4 keV is much smaller. It's a lower threshold than the Swift from BAT. So it's very interesting to detect the redshift gamma burst. And the localization accuracy is 12 arc minutes. It's a radius. So if you observe in optical domain, it's 20 arc minutes, the number that you have to keep in mind. The trigger rate is about 65 gamma bursts per year. And the second large field of view instrument is a GRM, gamma ray monitor, which is developed by in Beijing, in China. 3 gamma ray detectors. They are used to detect, to measure what we call the EPIC, the maximum energy of the gamma burst, which is missing information
in Swift. Then we have two now field of view instruments, the X-ray telescope, MXT, micro-channel X-ray telescope. We use a technology developed by Leicester, by the Leicester University in UK, of course, the Lobster Eye. It allows to have a cheap double quote, it's not so cheap in the end, but cheap X-ray optics. The field of view is at about 1 degree, typically 64 per 64 arc minute. And like this, we have a much better localization accuracy, so but we expect to have something between 20 and 10 arc second. It's again a radius here. So we plan to use MXT to refine the localization position of the gamma burst alert. And then we have the visible telescope, which is developed by Xi'an and Beijing, the NAOC in China, in Beijing. So it is a Chinese telescope. It's a 40 centimeter telescope, Xi'an telescope, the standard one, with a field of view of 26 arc minute. 26 arc minutes, just to remind you, this is the localization accuracy provided by Eclair. And we have two channels. We have no filter wheel on board, a blue channel and a red channel. And the idea, of course, is to follow the gamma burst in the optical domain. So we should be able to detect, to see a gamma burst up to redshift 6.5. And we plan to use it to have a redshift indication. It's not so nice. It's not so easy, in fact. But okay. How it works? What is our observing strategy? But it is exactly the same than Swift, in fact. So there is no miracle in this business. So you have to monitor a large part of the sky. When you have an alert, you have an auto slew on board, and you put your now field of view instrument, and you follow your gamma burst. In parallel, we have a VHF antenna all around the Earth equator. We send the information almost in real time, so what we call French Science Center, and you can receive all the ground telescope can listen this alert. I will be able to listen to this alert, not yet open, through the VO event network. There is nothing new here. And we have two telescopes, which are slightly more complex, as you will see, which are included in the system of the satellite. And this telescope will respond automatically to this alert and will disseminate through the GCN. So the idea is that we trigger the large telescope as a VLT, or I have to change this. I have to put NOEMA here. I'm French, so I have to show NOEMA, of course, here. And that's all. This is the standard way. Something which is even more important for me personally, because I'm working on the project since the very beginning, so almost 20 years ago. So here, this is integration of the payload on the satellite, on the platform in China. It is in Shanghai, in fact. So you see the VT here, visible telescope. Here you have the GRM, here. On Eclair, you don't see it, but it's here on the other side. So the satellite is now built. It is under test in Shanghai, and we expect to have the acceptance, the final acceptance of the satellite on the payload in December or January. If the acceptance review is successful, we hope so, the satellite is sent to the launch pad, the south part of China. And we expect to have the launch between March and April 2024. So we are very close of the end now. And after the launch, we have about 2 months, 3 months of qualification in orbit. And after, we start our life. So everything happens. Something also which is also very important for us is to have a powerful follow-up network on ground. So we are working very hard on this to include many facilities in this SWOM network. We have official partner, associate partner. You can see, I will come on this on the French ground follow-up telescope, which is named Colibri, but we have already agreement with several facilities, an official agreement with the node, for example. many other on Tasmania, IT also, many other facilities. SOX also. I can give you more details. The French follow-up telescope, so named Colibri. It's a joint development between France and Mexico. It's a fully robotic telescope. It is paid by Aix-Marseille University, CNRS and CNES, France, and UNAM and CONACYT, Mexico. The telescope will be will operate from the Observatory Nacional de Mexico in Baja California, in Mexico. So you can see the telescope. You will see by in operation in a few seconds. The property of this telescope is that it's 1.3 meter diameter. It's a brand new telescope. It has been especially designed. It's very fast because you can be in less than 20 seconds. 20 seconds is really the worst case when you have to do all the turn of the azimuth base. But you can see the telescope here. I could show the sound. It was at the very beginning of the project, and it's very accurate. And when you are on the target, you can be sure that your target is in the center of the field of view at few pixels. We have done a lot of effort to have a nice image quality. We don't have to forget your sensitivity is directly linked to the seeing and the image quality that you have on your telescope, on all the instruments. So we have a seeing limited, the median seeing at the observatory in Mexico is 0.8 arcson, which is almost, it's a good sight. And we have a wavefront error. It means the image quality that we have at the focal plane, which is in fact 50% better than the requirement. So we have really done to have a very sharp stars on our image. At the focal, it's a Nasmith. It's an Altas telescope. The Nasmith. We have two Nasmiths. So we have a field of view of 26 arc-minutes. We have 3 cameras in parallel. We have 3 bands simultaneously. So in the visible, we have Drago, which is developed by UNAM in Mexico. It's Mexico City, covering from B to SDSS Z band. The field of view, 26 arc-minutes, and the pixel set is 0.4 arc-second, sorry. And what is interesting that the image is very, very nice, even in the corner. So we have really done a huge effort on the image quality. And we have also an infrared camera, which is developed by Toulouse, by France. We have the sensor, it's a lean red sensor, it's a French, it's complicated, it's a complex story, but it is developed by Europe, so between France, CA, and also ESA. And it's an infrared sensor, and the pixel is slightly larger because it's a 2K per 2K, not a 4K per 4K. But an infrared sensor is slightly expensive. So, 2K per 2K is already not so bad. And the pixel is 0.6 arcseconds. So, we're slightly undersampled on KGR, which is the name of the camera. So, the Colibri was tested during 2 years in France at Observatory de France at OHP. And Colibri has left OHP mid of June. You can see the telescope here. For me, it was also very important because it was also a huge effort, and it is 16 tons. And now the telescope is in Mexico, in Baja California. And you can see the building under construction. It was in July, so it has progressed a lot since then. But it is a building at the observatory. Just to have the scale here, you have 8 meters. In fact, here. And you add the dome, it's about 11, no, it's 12 meters, the summit. For the expert, we are very close to Bootes 5, well-known robotic telescope. So we go in beginning of November to have the acceptance of the building, and after we start installation of the telescope. And so the observation we start in spring of next year in 2024. Just to conclude, I hope I don't have to convince you that scientifically the sky is rich of transients of many types. We have a lot of nice discovery. SWAM is the optimum follow-on to Swift, and Colibri is fully dedicated to the transient sky, so we will work for SWAM, but not only. We have our own scientific program. I see that Michel Denfeld is connected, so Michel knows this perfectly. I hope so. So the gamma burst alert from SWOM, but also we will follow the fast radio burst, gravitational wave, neutrino. It's a very fast telescope, so we want to use this property. So just to be clear, SWOM on Cobri will be in operation much less than 1 year. I cross my finger for the launcher because it's the last risk that we have. And everyone is invited if you are interested to participate to the follow-up or to participate to the science. So you can send me an email. You're welcome. So in particular for the students and postdoc, for the young guys, and scientists, of course, everyone is welcome. That's all for me. I just let you with the sky of Mexico.
Okay, thank you very much, Stefan. Nada. Yeah. And while she's walking here, I'll ask, what is your plan for disseminating the detections?
What is the plan for? I don't know you very well.
How are you planning to spread the alerts you find?
From SWOM?
Yes.
But it will you just have to listen to the GCN. So you will receive all the trigger, and you can apply your own filters.
Right.
We have a broker, our own broker on SWOM. So we will disseminate this information later. In fact, the broker is active already, and we're using this broker for other telescopes for internal test. It's not yet open to everyone.
Okay, good. Nada has a question.
I'm sorry if you mentioned this, but I'm not sure. Are you planning also to offer this the VOM satellite for triggers like TO observations in similar way that Swift is doing that now? And again, I'm sorry if you said it that I missed.
I'm sorry, I don't hear you very well with the microphone.
You should come closer here.
So, are you planning also to offer the target of opportunities?
Yeah.
So that,
Yes.
Okay, thank you. I was not
it's open. Well, it will be possible to submit some target of opportunity, of course. And also we will have a general program. So not the first year, because we have a lot of things to do the first year. But the second year, we will have a general program open to the community. There is some specific rule, but next year, I will join you. You can notice, Lukasz. I will join.
I'm writing it down.
But we can do details at that time.
Okay, fingers crossed.
Yeah.
Okay, thank you, Stefan. We have to move on to the next talk, so thank you for this. And the next one is by Thomas Weavers. And he's there, yes, Thomas, hi.
Hello, can you hear me? Can you see my slide?
We even can see your face. Yes, the screen is yours.
Okay, perfect. Okay, thank you very much. So thank you for giving me the opportunity to present here some work that I did on a Gaia discovered tidal disruption event, where I'll try to show you some cool things that we found. Since there is probably a very broad audience, what is a tidal disruption event? We have supermassive black holes at the centers of galaxies. We have stars in their nuclei, and these stars are undergoing two-body relaxation, which means that their orbits are being perturbed. And sometimes it happens that a star, as is pictured here in this image, passes very close to a supermassive black hole, such that the tidal forces of the black hole overcome the stellar self-binding energy, and then the star gets destroyed, or spaghettified, as we sometimes call it. And so you can see this process occurring here, where about half of the star is bound to the supermassive black hole, so of the destroyed star. And this will form an accretion disk, and so there will be accretion and ejection. So you can see here that there is, well, this is not a jet, but a powerful outflow that is emanating from this black hole. And so just as a kind of, as a kind of broad, big picture, why TDEs are interesting, why these events are interesting. They have a very high dynamic range and accretion rate. On the left here, you see a theoretical light curve where you have the time on the horizontal axis and the mass fallback rate. or the accretion rate onto the black hole on the vertical axis. And so you see that the accretion rate is initially highly super Eddington, but also it decreases by a factor of about 10 in a year. And so you can do a lot of things with such a case. You can test accretion disk models and measure the black hole mass and even the spin of the black hole with X-ray spectral fitting. You can study the powerful outflows that are thought to be produced after such an event. And you can even study supermassive black holes in their different accretion states, similar to what has been done for 40 years in low mass X-ray binary black holes. So generally, this is a probe of the 90% of the black holes in our local universe that we're not seeing if we're looking at AGNs. So they have very different merger and accretion histories. And so studying their demographics is a nice complementary thing to do. So then let's go to this cool TDE that Gaia found. It's called Gaia 20 CJK or 80-2020 KSF. There's a redshift of 0.09. It was discovered by Gaia Alerts, which is something that doesn't happen so often because of the slow cadence of Gaia. It was classified with optical spectroscopy, where we saw broad Balmer lines and helium-2 emission lines. And I'm showing you in this figure here on the right-hand side, the light curves. In the top, you see the UV optical light curves, and in the bottom, you see the X-ray light curves. And the horizontal axis is the same for both. And so Gaia discovered it. So if you look at the top panel, these blue points are Gaia. So Gaia discovered it. We went back to Atlas for photometry to find the rise or the peak of this light curve. So there's Atlas, there's ZTF data, and so on. But the interesting thing is that initially, while the optical is very bright, the X-rays, which are down here, we were lucky enough that Rosita happened to scan this part of the sky at the same time as the UV optical emission was peaking. And so we find this upper limit here. So the transient is initially optically bright, but X-ray faint. And so you see as time moves on, the optical light curve decays over about 200 days. This is very typical for TDEs. After about 230 days, suddenly this TDE becomes very X-ray bright with X-ray emission that is consistent with the Eddington limit of the black hole. So this is somewhat surprising in the sense that so we don't understand why there is this delay. This is not the first TDE in which we see such a delay. And so we're still trying to figure out what is happening, what is causing this delay. So we have a lot of NICER data from eRosita, also from NICER, which is an X-ray instrument on the ISS, as well as SWIFT in black here. And just this inset here shows the NICER light curve around the peak. So we have a very good temporal sampling, time coverage, over about a week around the peak. And so these are the observations that I will be focusing on in the rest of this talk. I just put on the bottom left here the Gaia BPRP spectra. I always find it very nice to see that TDEs are very blue. So you can see in the left here, this is pre-peak. And then in the bottom right here, this is the TDE. So you can see this very blue emission even in the Gaia spectroscopy. Okay, so looking at the X-ray spectra around the peak of the light curve. So what I've done here is I've taken all the X-ray data in between these two lines here, E1 and E2, and stacked them and created a spectrum. And I've done the same for E3 and E4. So these two epochs are separated by about 3 days. And so on the top panels here, you see the X-ray spectra. And so these are very typical for TDEs, very soft X-ray spectrum with a thermal continuum and a temperature of about 100 electrovolts. And so in the bottom, I'm showing you the ratio of this thermal model fit over the data. And so if you move to the right-hand panel, then you can see already by eye here in the top panel, but also in the bottom panel, that there is this strong absorption feature, which is highlighted in gray, which is not there initially. And so again, these spectra are differ by only 3 days. And so these absorption features are a typical signature of accretion disk winds. And so what we did was try to model this with an accretion disk wind. Or just to say, we also have, the previous spectra were about 200 days after the optical peak. We got another XMM Newton spectrum about 700 days after the optical peak. And this absorption feature is still there, which is perhaps somewhat surprising, but I'll come back to that later. So the X-ray emission, even after 700 days, is still consistent with being Eddington limited. So that is quite extreme, even for a TDE. And even though we're already 2 years past the tidal disruption event, there's still no X-ray corona, which is another interesting thing of this TDE. Okay, so these absorption features, an accretion disk wind is not the only explanation. So I don't want to go into too much detail, but we went through a lot of trouble to try and explain this with very simple models first. The takeaway is that pretty much nothing else works very well, or nothing else works as good as an ultra-fast outflow model. So an accretion disk wind, which is highly ionized and moving at about 0.15 C. So that's about 40,000 kilometers per second. So you can do detailed modeling of these X-ray spectra, and the result is in this table here. You can just focus on what is in this red box here, which are the wind parameters of the NICER spectrum and the late time XMM Newton spectrum. And so you see that this wind has a column density of almost 10 to the 23 per cubic centimeter, which is very high, which then decreases after about 500 days to something a little bit more moderate, 10 to the 21.5. The ionization parameter, which is a proxy for the ionization state of the gas, also decreases significantly. And this is expected because the continuum temperature of the ionizing emission also decreases by almost a factor of 2. But the velocity, even after 700 days, stays roughly the same at a blue shift of 0.15 C. So you have this very powerful disk wind that is there for at least 2 years following the tidal disruption event. So these values are very typical or very similar to the ultrafast outflows that we see in AGNs. But I'll point out that this is only the second TDE where we found and modeled an ultrafast outflow. And actually, this one that we found is 10 times more powerful than the previous one we knew, which was in Assassin 14 Li. And so kind of the takeaway here is that, people thought that ultrafast outflows from TDEs are probably not very important energetically in the evolution of galaxies, but actually maybe we should go back and make sure that is actually true or not, whether that's actually true or not. So just these plots here show again the X-ray spectrum on the left, and then the residuals after adding the UFO in the middle, and the absorption profile of the wind on the right-hand side. And so from this we can kind of see that there's probably transitions of oxygen 8, if you're interested in that are causing these absorption features. So this very fast variability on a timescale of about 3 days is was also somewhat surprising to me, at least. But actually, I went through literature and found that this is consistent with clumpy winds in in supercritical accretion flows of low mass black holes. So I thought this was really cool, actually. And then just as a final slide, so I mentioned that we were not sure, or it was assumed that TDEs are not important energetically for a larger scale feedback in galaxies. So when you model such a wind, you can determine its mass outflow rate, which is m dot out here, which is about 5% of the Eddington rate. All this material is falling in, but material is being pushed out at 5% of the Eddington rate. And then you can calculate the kinetic power of this wind and compare it to the Eddington luminosity. So you see that this is less than 1%. And you can calculate the actual kinetic energy that is injected into the interstellar medium of this galaxy. And that's about few 10 to the 49 ergs per year per TDE. So what you can do now is assume a TDE rate and say, well, okay, how many TDEs do I need in order to inject an energy that is similar to the gravitational binding energy of the gas in such a nucleus, which is the plot that is shown on the right here. So on the left axis, you see the number of TDEs to reach an injected energy similar to the gas gravitational energy. And so you see that you need, of order 100,000 or even 1 million TDEs. And so 80-20-20 KSF is this blue star here, and Assassin 14 Li is this orange star here. So you can see clearly that the outflow that we found was a lot more powerful than the previous one. And so you can take the number of TDEs that you need to do this and multiply this by a TDE rate, and then you get a time scale. So for a typical TDE rate of once every 10,000 years in a galaxy, the timescales for reaching this injected energy are more than 1 billion years. And so the conclusion is that, okay, probably TDEs are not really providing a significant contribution to that. But there are situations in which we know of that where the TDE rate's actually substantially higher. And so this scales pretty much linearly with the TDE rate. And so if you just increase the TDE rate by a factor of 10, which is the case, except for example, thought to be the case in E+A galaxies, then these timescales become of the order of several 100 million years. So this is the most powerful outflow that we know of now, but we only know 2. So if there are outflows which are another factor of 5 or 10 more powerful, then you're kind of in business in really making the gas in these nuclei more turbulent, preventing cooling. So you might not need a long-lived AGN phase to do that. It's kind of the tentative takeaway, with the caveat that we need to just find more TDEs with UFOs and study them in more detail. So I'll stop there, and I'll just conclude by saying that Gaia is still providing us with very cool transients. So thanks a lot to everybody who's still doing it, and I'll be happy to take any questions.
Okay, thank you very much, Thomas. There's a couple of questions. Rupak, Ilse.
Thanks, this is Ilse. This is a very interesting talk. I was wondering about the last plot that you showed about the energy distribution into the galaxies. Do you assume that this is a uniform or a non-collimated outflow, or do you assume that it's more jet-like or more collimated because it goes really fast?
Yeah, so the assumption in these calculations here is that it is isotropic. That is for simplicity, and yeah, because we don't really know the covering factor at this moment, even in AGNs. I think this is a very debated topic. What is the covering factor? But so something that to keep in mind is that here we're assuming that there are 10 to the 6 TDEs, and these stars, they come also from isotropic orbits in the nucleus, and so you do not expect everything to happen in the same plane. And so I think in the end, this energy that is given to the interstellar medium will be roughly isotropically divided.
Hi Thomas, this is Rupak. Did you see what is the UV emission? I mean, did you see any line like frozen line or something?
Sorry, can you repeat that? I think the microphone is not on.
Yeah, you have to come closer to here. The microphone is actually here.
Did you see any fluorescence line? I mean, what about the UV emissions? I mean, our lines, you have a strong X-ray, so that's why.
Yeah, so we only saw this UFO feature after the fact. And so at the time, I can show you the light curve. So at the time that we were seeing this UFO, basically the UV optical was pretty much gone. So sadly, we do not have any constraints on that.
Okay. Thank you, Thomas, and thanks for joining us remotely. And we move on now to Laurent Oyer, who will tell us about Gaia variable stars in very general aspect. Laurent, the screen is yours. But we don't hear you. We can't hear you. You have to unmute. Sorry.
Okay, that should
That's
work.
better. Okay. Hi.
Hello. First, that is a pleasure to be invited. I wished I could have come, but I'm at another, I'm at a PhD school and I have to teach tomorrow 5 hours 30. So it was quite an exercise to speak about these topics, and I could take benefit of these 2 talks to do a presentation for your Science Alert meeting. So thank you. And that is my usual slide of the Gaia mission. It's a systematic multi-epoch survey, a cornerstone of the European Space Agency. It's measuring more than 2 billion stars. It measures position, brightness, colors, radial velocities, spectra. It was launched in 2013, and the end of data acquisition is in 2025. No more, there is a typo, no more coal gas at this time. So that's a real end of the mission. For a 10-year mission, on average, there will be 140 times in each of the 9 CCD, in each BP and RP CCD, and 80 times in the radial velocity spectrometer instrument. The data is public through data release. The DR4 and DR5 will be in 2025, and in fact, the terminology of ESA is no later than 2020, not before the end of 2025. That's the correct terminology. And DR5 is foreseen in 2030. So Gaia is a time domain census, and it's a mission of superlative, also for variable stars. So you see there is a booming era of optical surveys. I put several here from ground-based, from space. I put in bold the surveys I touched. I analyzed some data, but in a way, Gaia is among these surveys quite outstanding. So why is it outstanding? Because it has an unprecedented astrometry for so many stars. There are 3 instruments on the same platform. You have a quasi-simultaneous measurements in these different instruments, which facilitates the analysis. Then you have the multi-epoch measurement over the entire sky, whole sky. The number of measurements, there are many data. So for the 34 months of DR3, it's nearly 1 trillion CCD measurements. The time base will be, if all is going well, 10 years, and the frequency precision will be very high for periodic objects. So that's a very interesting point for pulsating stars. There is a high dynamical range from the brightest sources. The brightest in DR3 is 1.7 mag, to magnitude faint down to 21. There is a time domain selection function because of the scanning law, which is regular. It can be determined. And Gaia is in space with some stability, and the whole celestial sphere is accessible from one platform. Furthermore, there are the cyclic improvements of the systematic analysis, more data, better calibration, better detection of outliers, and enhancements of problems identification. So I was at EAS in Krakow, and the Kistler-Pattig showed this diagram of the number of publications per year over the years of the different ESA missions. And that's the first time I was seeing this diagram. I think it's stunning. We see how Gaia data is used. Why do you have this? Because it's concerning fundamental measurements of celestial sources, like the position, like the brightness, the colors, and also that will be maybe a bit later, but with the spectra. So these cyclic improvements, when you look at this, you have DR1, which was in 2016, DR2 in 2018, DR3 in 2022, and you have the other data releases. And you see that there is, at every data release, we enlarge the number of stars that will be published as variables, and also the complexity. In the first data release, there was only the G band. Then in DR2, we had G band, and we took into account astrometry and the BP RP integrated. In DR3, additional to this, we added radial velocities for some sources, and we added RP spectra. And in DR4 and DR5, we hope to use all the possible information. So we can go from more simple to, at each step, more complex. We had 2 variability types in DR1, 7 in DR2, 25 in DR3, and we will try to reach all variability types known, and we will try also to have unknown variability types discovered for DR4 and DR5. So this progressive and iterative approach is really lowering the risk of doing something wrong. So if you look at the variability tree, these growth of number of variability types, DR1 was concerning mostly Cepheid and RR-Lyrae. DR2, you had BY Draconi stars, so spotted stars, and LPVs, and also Delta Scuti stars. And in DR3, you cover globally all these groups, so we start to be quite complete. And some groups are put together in one basket. So the Gaia data, that's, as was mentioned before, diverse data. So you have unprecedented astrometry, unprecedented photometry, unprecedented spectroscopy, and you have an enormous amount of data. So that's at the end of the mission, that will be many trillions photometric measurements. And in order not to be submerged by this also in the analysis of variability, you try to do this thanks to machine learning. But what was a bit special when you look at the development we did within the Gaia consortium, we have a part where we have the approach of machine learning, and then we have on the other side a human expert in certain specific studies. When you look at other surveys, either they took the machine learning approach and they process all the data, or the other, like Ogle, they go directly here, or in ZTF, we would say that they have an approach where they select topic, they use machine learning, but it's all conducted by, I would say, human experts on the specific topic. So it's a bit specific, this approach in Gaia. In DR3, what do we see? It's the largest set of classified variable sources on the whole sky. And you see that the largest fraction that is pulsating stars, then comes variability from rotation, and then eclipsing systems. We have 10.5 million variable sources which are classified. You have 9.5 million variable stars and 1 million AGN. And also, thanks to spurious effect, which was, that's also what is amazing. Suddenly you see there is something wrong. You have time series which are variable, but there is no variability. That's because of the way Gaia is taking the data. You have 2.5 million galaxies that were able to be identified through this kind of spurious variability. So the DR3 articles related to variability, we see that we published 16 articles. I won't go through them, but on many different topics. And Gaia DR3 is breaking many records. As I said, it's the largest classified set over the whole sky, but we break the record on the number of LPVs, we break the record on rotation modulation, we break the record on eclipsing binaries, we break the record even of RR-Lyrae stars over the whole sky. And here are some of the different types, beta Cephei, BE stars, etc. That's all these sources we classified. And what was also important is to try to determine the completeness and contamination. So here is one table. There are other tables for other types, but where every group tried to see what were the level of completeness and contamination. We believe, or I believed, I pushed these different groups to be able to determine these numbers. So we see there are large variation. There are objects which are not very complete. You have other where there is a lot of contamination. And we try to improve. Obviously, these are estimates. And we see, for example, for RRL rays, the faint end of RRL rays, thanks to the work of Sozinski, we see that the contamination is a lot higher than thought. We have also a summary of properties of these variability types with amplitude in terms of trimmed range. We have also the median BPRP, also the time scale or a period of these objects. So globally now you would be able to do a model of the Milky Way, a full model of the Milky Way using these data. And I mean the Milky Way in terms of variable stars. So some results on the variable source. What is important to know, we see there is a bit of a confusion in the literature. So for a variability type, there are two sources of information. There is the machine learning classification, and there is the human analysis by experts following this machine learning. And so if you want to study, for example, RRL stars, then you have a list of RRL stars, which is coming from the machine learning method, and you have also the specific study of RRL, and sometimes that's not matching. So that's important to know. So people should really look at all these tables in the archive when they look at this. You can do, I didn't show here a HR diagram of the variable from the parallaxes, but you can do also HR diagrams if the object is considered to be at fixed distance. So here is the LMC, that's the paper of Xavier Loury in 2021. And globally, here is the content of variables in this region. So I think I superpose the two. I think you can see. And we are able to detect delta Scuti stars, RRL stars, Cepheids, which are here, long period variables, BE star and eclipsing binaries a bit everywhere. You have also Arcorone Borealis stars, gray point, I think, here. And for example, what we see here is that in LMC, there is a quite sharp edge to the tip of the red giant branch. It should be noted that that's a side note. So globally, the stars at the tip of the red giant branch, they are nearly all variables. So that's not very well known. It's curious. It should have been well known for decades, but by the community doing the tip of the red giant branch. And so globally, the variability, it helps to understand the properties of the tip of the red giant branch. And in fact, it tends to reconcile the distance scale from the tip of the red giant branch with one of Cepheid. Now, on the radial velocity, what is fantastic with Gaia, you have here the G band, the B band, the R band, and you have also radial velocities there. That's the largest sample of stars having radial velocities for Cepheid and RRL ray. Here are the RRL rays. So every plot here is the one star with a G, BP, RP, and RV time series. What you can do with these large number of RRL rays, you can look at the period amplitude diagram. It's very impressive when you worked for some time on these stars. It's kind of mind-boggling. And from the light curve, you can estimate, for example, the metallicity of the RRL rays. And here is a sky map where you plot the RRL rays and the metallicity. And you see that the the global picture, it's quite amazing. It's working. You see that the SMC is more metal poor than the LMC, and you have the region here in the bulge where you have more metal rich. So things you see also the Sagittarius stream here, Sagittarius galaxy. Sorry. With obviously combining photometry and astrometry, you can look at the period luminosity of RR stars. Here it's done in the estimation are done in infrared magnitude, in fact. When you look at these stars, okay, that's there is noise here, and then in DR1, that was Hipparcos, then DR1, okay, that's starting to be nice, DR2, DR3, and that was, you really have a nice and tight relation, even for RR rays. And you can use, this was done in optical, you can use this to look to really do a mapping of the stars of the RR rays throughout the Milky Way. And you have little streak. I don't know if you see, that's the globular clusters. We go away. You have the LMC and SMC, and you have the Sagittarius galaxy, which is appearing, and with the stream, which is appearing for the RR rays. It's quite, it's very easy to do, and it's quite amazing to see this. Okay, you can do also other things with period luminosity relation. We looked at delta Scuti stars, and so to my knowledge, that's the most extensive and precise empirical period Wesenheit relation of delta Scuti stars. And so what you see, for example, it's difficult to have one linear relation. Maybe you have a quadratic, or you have to take a broken relation where you have two regimes. So that's, they also obey a period luminosity relation. You can take now the RP spectra, and you can look here at the HR diagram. You have the loop of the star of an LPV, and you have the color variations here, the G magnitude here, and you have the spectra, which is varying along the phase. And so from the molecular bands here, you can select, determine the nature, if that's carbon-rich or oxygen-rich long period variable. And so that is published in DDR3. We have a classification of more than 500,000 carbon-rich long period variables. So that's one of the exploitation. One of these, a thing where you merge a bit everything together, also the time series of the RP spectra. Small is beautiful. That's a diagram that I always love to show, because one of the Geneva, obviously I'm in Geneva, well, I'm in Geneva, that should have been said, at the Geneva Observatory, and obviously Geneva Observatory is very well known for the exoplanet. So when I started Gaia, somebody from the group of exoplanet told me that with Gaia, we would discover zero exoplanet. I could not believe. We had a long argument, and now I'm very happy that I prove him infinitely wrong. We have 214 candidates, 173 are known system, 41 are new system, and we have 2 confirmed cases. Here they are. You have in tight light points, you have TeV photometry, and you have the merging here. What is important is that G, BP, and RP are used. All the 3 bands are used together. And here you have the transit, which is very, very nicely described in Gaia bands. So a little warning, there are 2 tables now in the Gaia archive about the planetary transit. There was a mistake at a point. Also, there is a collaboration with the NASA TESS mission to confirm the transit or identifying background eclipsing binaries. And with Gaia data on the candidate of tests, we can say that 5% are wrong. It's not exoplanetary transits, that's background eclipsing binaries. And 5% we can confirm that indeed we believe also there is a transit. So that's work done by the Tel Aviv team, who is part of the consortium. Tzvi Mazeh, Shai Zucker, and now it's Avraham Binnenfeld. And so there, this is with the cycle 3 DR3 data. So soon we will receive cycle 4 data, and this is a fraction because we were working only with 34 months. Now we will work with 66 months. So these numbers will, they won't double, it will be more than 10% each. So probably for 30, 45, 50% of the case, we could do a good judgment on the test data. We can also push the limits on the small amplitudes. That was shown by Connie Arts in EAS, where we can compare what Kepler is doing for Gamma Doradus stars. And we see that that's the amplitude of Kepler, amplitude of Gaia in millimagnitude. And we see that we can reach just a variability of few millimagnitudes. So this gives hopes that in DR4 and DR5, we will be able to identify millimagnitude phenomena in Gaia data. Another point which is important, it is the multiperiodic behavior, also that's work in the paper of Derrida, where there are, here you have on the left Kepler data, that's one star, and you have two frequencies, so that's multiperiodic behavior, and you have Gaia data here, and so that's the first frequency and the second frequency. And what was amazing is that in Gaia data, you are finding these two correct frequencies. So this gives some hope that it opened the door of a multiperiodic analysis in Gaia data. This is something I didn't believe we would be able to do many years ago, but the quality of the data of the photometry is remarkable. Obviously, there are problems. Here I'm showing the glass half full. There is also the empty part. Maybe I won't go into too much detail. It might not be easy, but it opened the door. And if really that's advanced there, it will be quite amazing, because here we are finding these two periods with only 40 measurements. If you count the points, here the phase is going from 0 to 2, but if you count the points, there are 40 measurements. It's really amazing. For the recent event, so stay tuned. Next week, there is a focused product release. So I remind that in LPV, we have a record there. We have 1.7 million long-period variables. We do a selection. We have 34 months, and we are producing for this data release 9,000, nearly 10,000 stars with radial velocity time series. So here is an example. You have the radial velocity and you have the different photometric bands. So again, this is a record. That's the largest sample of stars having LPVs having radial velocities. We have also, I think that's something that is dear to Łukasz, and I think it's very important. We know that microlensing, the effect in photometry is 1 over the impact parameter power 4, and the astrometry is 1 over the impact parameter. So the effect of astrometry is felt well before and after the photometric effect in the astrometry. And combining the two, you are able to solve the system. And it was shown that a hint of astrometric signal in this Gaia Science Alert, the Gaia 16 AYE. I was always hoping that was EIE. I could add the R, but okay, so that's numbering is a bit different. But I see always nearly my name in this object. And so we should remind here that that is the microlensing is the only way to detect single black hole. So having combining photometry and astrometry will be able to lift the degeneracy and determine the mass of the length. So that will be extremely interesting, and we hope that we can converge in DR4 for this analysis. Variable star in the HR diagram. Yes, so there that's, I still have a few minutes, I will go very quick. So this is the HR variability. I call this the Pollock diagram. You have pulsating stars are bluer when they are brighter. BE stars are redder when brighter, etc. And so we thought that we would do a citizen science project with this, and we finished the first campaign. And in fact, we are looking at the cases in DR3 which are published, and we are looking for confirmation, or sometimes when we have doubt between the machine learning and the classification, we are using the citizen scientist. And globally in Gaia, we have machine learning and expert astronomers, and now we add citizen scientists, and it had been proven very useful. So for example, you have a star here, that's here is the link. You have the time series here, the magnitude as function of the time. Then you have a tutorial. And then what we do here is we fold when the star is periodic. So this is quite, it's like the old helmet of the bobbies, the policemen in UK, I think a bit. We see that in 9 days period. We put also the motion in the HR diagram. There is kind of loop here, it's very red. And we put also the position in the Milky Way. So we see the star there is beyond a galactic, it is in the disk and beyond the galactic arm. So we can suspect that it's a very reddened object. So here the solution is quite easy. I would say it's a Cepheid. And then you can go in Done and Talk. And then you can access this information button, and you have the source. Once you said done and talk, you can't look at the source before you classified it. It's very good. So you have the source ID. Here you have the classification by the machine learning algorithm, and you can also go to ESA-Sky. You go to ESA-Sky, then you can go to Simbad. In Simbad, you see it's already a known source, a classical Cepheid variable. You can go in the literature, for example. And you have also the comments, which are very nice to look at. You have here a comment of one of the best classifier, a beautiful Cepheid. The Hertzsprung progression in the Cepheid class is very interesting to study, yes, and you have many comments. And we start the second campaign, where we are looking mostly at when there is overlap of the classification, where people disagree on the classification. So in conclusion, yes, I think I'm not too late. Gaia is a real-time domain machine having outstanding results in the time domain astrometry. You can position the variables in the HR diagram, having variability strips. You can have time domain spectrophotometry. You have the largest catalog of classified variable. You have the color magnitude variation. You can classify carbon-rich stars thanks to the RP spectra. You can reach quite small amplitude. You have this citizen science project. You have also the radial velocity, which is complementing the picture. Now we have the largest sample ever of sources of radial velocity in Cepheid, rarely and soon in LPV. And you have also, obviously, the spectroscopic variance. In DR4, an avalanche of data, and I think people need to be ready, those who are interested in this topic of variables. Thank you very much.
Thank you, Laurent. Any comments, questions to Laurent? There is one on Zoom. Michel.
Yes, hello, Laurent. Maybe I missed it, but when a star is crossing the field of view, it crosses 9 CCDs, and the crossing time for 1 CCD is 4 seconds, if I remember correctly. do you have information from variability from one CCD to the next, that is on a time scale of a few seconds?
Yes, yes. So the time series of the per CCD information is not published yet, but for example, in DR2 and DR3, we used this information. Unfortunately, there we see that we detect some instrument effects as a variability. So that's one slide I wanted to add at a point, but I removed it because I had already 2 slides. So globally, this information, it's every 4. I think I have a little doubt. The integration time is maybe 4.2 seconds, and to the next CCD, it's 4.4 seconds or 4.5 seconds.
Yeah, yes, that's what I remember. Yeah.
So that you have this sequence, and indeed you can study if there is variability. If you look at a paper we published for DR2, we see, for example, an eclipse happening over these 50 seconds or over tens of seconds. You can see really the trend from the eclipse. So you are able to detect this type of variability at the second level. It's very interesting.
Yeah, thank you.
Okay, thank you. I'm afraid we have to move on to the next talk. Thank you very much, Laurent, for joining us despite your busy schedule. So I hope to see you sometime soon. And now we kind of continue on the topic Laurent mentioned within his talk with Dr. Katarzyna Kruszyńska, a very new doctor. That's why I emphasize this. She just defended a few months ago. Katarzyna is now in sunny California and is going to tell us about microlensing in Gaia. Kasia, the screen is yours, but we don't see it yet.
Hello, let me just try to share my slides. Slideshow.
First you need to share the screen.
Yes, yes. Okay, can you see my slides?
Yes, it looks good.
Okay, fantastic. Then let me welcome you, everyone. Hello, it's great to see you even in a virtual form. My name is Katarzyna Kruszyńska, and I recently graduated from Astronomical Observatory, University of Warsaw, and I'm currently, I just started a month ago, postdoc at Las Cumbres Observatory. I wanted to show you some highlights from Gaia Science Alerts, but also then expand the topic and show you why is this important and maybe some steps for the future. So first of all, I think I am the first person to talk about microlensing. So I will give you a very short explanation how this phenomenon works. It occurs when we have a massive object of the mass. The mass can be from the planet to the mass range can be from the planet to the black hole, passing in front of a star within our galaxy or a nearby galaxy. That way we can see a very characteristic shape in the light curve shown in here. And this phenomenon also causes a deflection of the path of the observed star, shown in the blue line here. Both of these aspects can be observed if we have the right instruments, and the change of the light is obviously a photometric event, and the change of the position of the star is the astrometric effect. Because we want to observe both of these effects, astrometric and photometric. That's why I focus on Gaia for this project. And this means that we have to include both strengths and weaknesses of Gaia. So first of all, Gaia is currently the only mission which can provide both photometric and astrometric time series for millions of stars. And this allows us a potential for discovering multiple astrometric microlensing events, which so far has been done only for a handful of events. This is very exciting, especially because the astrometric time series will be published for the Gaia Data Release 4, which is still a few years away, but stay tuned and start maybe preparing your pipelines for it if you're interested in microlensing. And Gaia also is one of the only missions which observes the entire galaxy, both parts of the disk as well as galactic bulge. It also provides 3-band photometry, which is very good, and it can help us change if check if the change the light is achromatic. And it provides a low resolution spectra, which for Gaia Science Alerts has been very useful for example, classification. It has its weaknesses, which is low cadence. On average, Gaia observes only 1 point every 30 days, which is for microlensing, which is usually dominated by very short, short events of the time scale of around 30 days. It's not very impressive. However, and this cadence goes even lower for events in the galactic bulge, which is the treasure trove of microlensing. So that's kind of sad, but hopefully we can deal with it. And this is where Gaia Science Alerts come in. So there are 2 channels of publication of Gaia microlensing events. One is Gaia data releases, which comes every few years and publishes the archival data. But we want to focus also on ongoing microlensing events, and that's where we use Gaia Science Alerts webpage, which I think is very familiar to all of you. This is the fairly current status of the Gaia Science Alerts. As you can see, we have over 500 events from the entire Milky Way. Also, a few candidates from Magellanic Clouds. Well, we will continue to detect such events until the end of Gaia. In order to cover the gaps that I talked about, the 1 point every 30 days, we use the follow-up network, which is presented here, and I think Łukasz already talked about it a little bit. And we use 2 services, one of which is Black Hole Tomb, which is very familiar to you, and soon we'll have a new version will be available. And for these events, this usually focuses on a selected, on a handful of events, which, well, not handful, but on the events which are selected by the users, and then they can be observed by a multitude of different instruments, such as both by amateur astronomers, professional astronomers, and robotic observatories. There is a second project which is also ongoing. It started back in 2020 or 2019, if I remember correctly. And it's Omega 1 and Omega 2 key projects, which are key projects of Las Cumbres Observatory. And their goals coincide with the goals of observing microlensing events from Gaia. They focus not only on events detected by Gaia. However, Gaia is a great source of knowledge on what is going on in the galactic disk, which is not observed traditionally by traditional microlensing surveys. I will talk about Omega 2 key project in a bit. This is a few highlights of microlensing events with follow-up that you have gathered over the years. Some of them are analyzed, will be published soon as papers. Some of them already have been. This is the slide that I shown last year about a catalog of microlensing events from 2014 until 2021, which had over 400 events with preliminary models and preliminary classification. You can find it under this address if you need. However, I started preparing an article about this, and I wanted to expand it until 2022. And in order to do that, I also wanted to make this the preliminary model more reliable, and to include all of the follow-up that was gathered by both Omega project and the follow-up, which is available in Black Hole Tom. So if you have observed any microlensing event, which was alerted by Gaia Science Alerts, please add your data to Black Hole Tom as soon as possible, because otherwise I will not know it exists, and I couldn't include it, this data set into the article, and you will potentially miss, well, a great opportunity to showcase your the capabilities of your observatory. So please do it as soon as possible. So as I said, microlensing can detect objects which have mass. They do not need to, the lenses do not need to produce any lines. So this could be a wonderful tool to observe black holes. I'm sure some people already mentioned that, and I wanted to maybe stress why it is so important. So first of all, there are two major problems that we have when it comes to the stellar remnants. First of all, we don't really know what is the proper stellar remnant distribution. We don't know how massive the black holes or other remnants can become. And if there are things which are known as mass gaps, which I'll show you in a second, and we do not really know if that's only an observational effect or is it something that actually exists in nature. These things are heavily biased. We have simulations, but they are heavily biased by our currently existing observational data, which comes from several techniques. Another problem is the stellar remnants velocity distribution, which is somewhat well known for things that emit some type of electromagnetic radiation, such as neutron stars, but we have very little information about it when it comes to black holes. So this is the plot that illustrates the first problem, which is the mass problem. And here I have marked in several different colors the techniques that we have used in the past to detect the masses of stellar remnants. Starting with, well, white dwarfs are lumped in together because they still emit a lot of light, some light, so we can observe them. And Gaia has been proven to be instrumental in this regard with producing one of the largest, well, I think the largest catalog of white dwarfs known to date. Secondly, the second largest group we have is our gravitational waves, marked in yellow in here, which, as you can see, is several orders of magnitude smaller. Detections from this technique is several orders magnitude smaller than the ones coming with white dwarfs. However, in here we can only observe distant sources, not from our galaxy, but many light years away, and also these are binary events, which means that they have very specific type of evolutional channel. This technique will not tell us what is happening to a single star or a single black hole, which may have been produced, might have just evolved like that through its whole life and become a solitary black hole, or maybe it was ejected from its original system. Third, and I think historically the oldest way to detect stellar remnants is the XRB, X-ray binary systems, which I split into two groups. I have lumped all of the known neutron stars in here, which includes X-ray binaries, and also we have high mass X-ray binaries, which are basically black holes, which are consuming something. These are systems again which exist in multiple. Well, they have at least one companion that they consume currently, and we can observe them as they form the accretion disk, which generates light. And again, this is a very distinctive kind of channel of evolution for such sources. The smallest group of these is microlensing, which has been, has his renaissance in terms of detecting black holes in the recent years. The results are shown in here in blue. It's very small. However, there is something in here which is called the first mass gap. And in this region, we do not expect to observe any, neutron stars or black holes. So basically, the first mass gap is the gap between the oh, sorry, I actually see that the mass gap should be in here. No, wait, here. Anyway, sorry for that. The mass gap is the gap between the mass of the theoretically largest, most massive neutron star and the least massive black hole. In the past, this gap has been detected by the X-ray binary community, and there has been suggestions that this may be only an observational effect. If that is true, we do not know so far because we do not have any other techniques to reliably detect black holes in this region. There's also a second mass gap, which is connected to the Perlin stability supernova, which comes in the very high mass range. However, this is currently out of, this is not the mass range that the microlensing can detect, at least right now, maybe in 100 years. So moving on, this is the velocity problem of dark remnants. Here in blue, I mark the neutron stars. This is where I assume in the neutron star community, a known transverse velocity distribution known for a catalog of several hundreds or thousands neutron stars known from the Manchester catalog. And for black holes, we have only one little detection, which was possible thanks to combining both photometric and astrometric data for a single event, which was detected several years ago by both Ogle and Mola teams. And there were two teams which gathered astrometric data using Hubble Space Telescope. And through that, they managed to solve this system and find out that the lens has mass of order of 8 solar masses. And combining the photometric and astrometric data, authors of the Mruz et al. Paper managed to measure the direct transverse velocity. This is the only measurement we have for a single stellar mass black hole so far. So how to measure the mass of a black hole when we use microlensing? For this, we need long events. When such events that are so long that we have to include the movement of the Earth into our microlensing model, and this creates these very characteristic wiggles in the light curve, which is shown in here for the Gaia 90 decay event. And if we have a long event and we can detect these wiggles, we can measure something which is called microlensing parallax. This we can measure from photometry. If we also have astrometric data, we can measure something which is called the Einstein ring radius, which basically tells us how, which is proportional to the mass of the lens. And if we have measured both of these values, we can directly measure the mass of the lens. And this is how the authors of that, the people who managed to detect that single solitary solitary black hole that I told you about in the previous slide, managed to measure its mass. So it has been proven in the past to be a very good technique to detect such elusive objects. And I tried to use the same approach using Gaia at least to find the candidates for dark microlensing events. In order to do that, I used two catalogs, one gathering events from Gaia data release 3, which were observed between 2014 and 2017. And the other catalog was Gaia Science Alerts. Well, it shouldn't be 2016 really, but the first event we have is from 2016, which has events up until 2021. Only 8 events were in common, so that's a little bit sad for both surveys, because if the event was not detected by Gaia Science Alerts, we couldn't get a follow-up. However, I still managed to find some external data from other surveys. For this, I created I've processed this data in several steps, but the final step was to go through 30 events, which I selected in the previous step, and for each create the most reliable solutions. In many cases, these solutions there were multiple solutions, which if you have photometric data, it is very hard or impossible in many cases if you don't have enough data to distinguish between them. So I use both of these solutions as is in my analysis, and I tried to using galactic model and some information about the movement of the, well, I assumed source in these cases, because I assume the lens is dark, so what we observe in Gaia in terms of movement is going to be the source. Using the data, this type of data, I tried to estimate the mass of the observed candidate dark lenses. And here in black points, I marked the observed, the measured data. As you can see, my technique is not very precise. It provides a very wide range of masses for many events. However, it shows that microlensing actually can be sensitive to the mass range of the mass gap, which is very exciting, because then we can check if this is actually something that exists. And if not, then what is in the mass gap? Maybe our theoretical models have to be adjusted. Second thing that I wanted to show, which is also exciting, is the estimates of the transverse velocities. However, in these cases, as you can see, there are maybe we can see two groups. Ones with higher velocities, closer to the known velocities from neutron stars, and ones with lower velocities. This is also something, well, first of all, we expect black holes to be moving much slower in many cases, but also there is some tension in the neutron star community where people model binary neutron star systems. And some people argue that neutron star natal kicks, which occur when the neutron star is born from a supernova, cannot be too high, because otherwise the binary system would not survive and we will not be able to observe it as a gravitational wave merger. And these are the results. So technically there should be objects which have the mass of a neutron star, and they have a lower velocity, which should help it to survive in its system. However, there is a caveat, and I wanted to have a slide for that. So these results that I have shown you are only as good as our assumptions, and heavy assumptions have been done in order to do that. First of all, I assumed the stars, the objects shown in here have the velocities expected for the galactic model, and the galactic model was not very complicated. It was and the second of all, I also used some very heavy assumptions on the possible masses of the system. So in order, and also as you have seen, the data in many cases could not distinguish between several different solutions. So in order to actually get the proper measurements of these candidates, we have to combine these results with the astrometric time series from Gaia, which is going to be available in a few years. And this will be the final test and the final that will produce the final results for our sample. I know that the analysis is going on, and it is produces very promising results. However, we will have to wait still a few years to see it. So finally, I wanted to talk for a second about my new work, partially, which is still important for this community, for Gaia Science Alerts community, which is a Mega2Key project. It is somewhat continuation of the old key project, which was where the PI was Etienne Bachelet, and the current project is led by Rachel Street. It is the project that focuses microlensing events coming from different surveys, classical microlensing surveys such as Ogle, MOA, and formerly KMT, but not anymore. And also like the surveys which are not focusing on microlensing events, which are such as Gaia Science Alerts or ZTF. Newest edition is Black Gem, and hopefully in a few next months we will be able to include those alerts too. Omega-2 Key project has expanded aims compared to the previous edition of this program. Now it only focuses not only on planets, but also or binary stellar events, but also on long events and on brown dwarfs, which are all long events, which is connected to black holes, and brown dwarfs is a very interesting population, which can be only detected by, in many cases, can be detected by microlensing, and it's also a population which is important for the planetary community and the communities which try to understand what type of masses are available in our galaxy. It uses an automatic observation submission system, which is available through TOM Toolkit. It has two types of modes, one which is high cadence mode, so the cadence is roughly from every few hours until up to every few minutes for binary and planetary events, especially if there is an anomaly going on. And there is a low cadence observational mode for long events, which suggest a dark lens candidate, and where the cadence is of order of a few days. This project uses microlensing observing platform, which is called MOP, shown in here. And it is created during through MOP Toolkit, and it was first created by Etienne several years ago, and now it is expanded by other members of the team, including me. This is the recent very exciting event that we managed to follow up last month, and as you can see, it's if you're familiar with black hole TOM, this should look similar too. This is a project which uses only Las Cumbres Observatory as its main source of observations. However, if by chance you have observed this event, well, then first of all, upload this, or any other microlensing event, then please upload it to Black Hole TOM, because in the future, hopefully, we will maybe create a bridge between those two projects, and then it will be easier to include the data for such events also in MOP. And I will maybe stop here, leave you with this summary slide, and maybe go to questions if you have any. So thank you.
Okay, thank you. Questions, comments? Wait. Anyone? It's the last one of the day, but there is another.
Hey, Kasia, nice to see you even online.
Hello.
I just want to comment on what you said regarding the first mass gap. I mean, it is being filled up by the detections from gravitational waves emergers. So, you know, because you said that it's empty, it's not, and it's also plotted here. So the
Yes.
Between, so it's from the first 9 that you have there to the 5th one. So the mass from 2 to 5.
Yes. However, the detection rate in this range is very low, as you can see, because this is 10 and this is 1. So the detections are rather of order 1 than hundreds or
of course, but
tens.
they are confirmed detections in that mass gap.
Yes.
The previous LIGO work around. So just wanted to make that clear.
Thank you.
Okay.
Anyone else?
I just wanted to emphasize something what Kasia said, that indeed we're trying to make MOP and black hole talk to each other and especially share data, and this is something what Rachel has mentioned already. That's kind of in order to avoid duplicates and also combine the data, make it even more powerful, especially that, you know, in some areas the scientific areas overlap, and then there could be data which can be shared. Right. I don't see any more questions later Zoom or in the room. So I'd like to thank everyone for this session first and then the whole day today. But before we disperse, there's a significant announcement for people in person here. Tomorrow we don't meet here. Don't come here to this room. We are going to the cinema. There's a cinema at the -3 level here in this very hotel. You can enter it from the elevator or from the outside. And apparently we're in the cinema room number 2. I put the info on it on Slack and on the program. So if you see someone who doesn't know about that and wandering around here, I think there will be another conference here, so they might be surprised. But we meet in the cinema tomorrow. Okay? And we're going for the concert if you want to join us. So to see you all there. Thank you, and I'll stop all this streaming and so on. And thank all the speakers. Bye-bye.